Yes, let's start, and we can stop and talk between. Okay. So before starting, one question. Any one of you here use any model explainability or interpretability before? Anyone you did it? Oh, good. 1, 2. Okay. Most of them didn't use that. So maybe you can use after this, and every coding with you means after a couple of hours. So you can just click and do that. Change the data, and it means we can do very easily. And that's the reason we all we made for you everything. So okay, let's start. Maybe okay here. Okay. Show a hands-on tutorial towards building explainable machine learning using SHAP, GINI, LIME, and permutation importance. And that's all not true because we have many more after these. So let's go and talk with that. So today's agenda is, and we start with an example because many of you do not know how to use and why you use the explainable machine learning, and we can go for a little bit of example, and that is our research, and where we use that explainable machine learning. Then we can go introduction and to interpretability. Remember, the interpretability and explainability same. Many people, they try to differentiate both terminology, but you could say it is same. Means you could see that means after the presentation same. Then it's the coding time. It's the first coding time. It's the 2 codes, means 2 collab code we already made for you. Then we can go SHAP. SHAP is very detailed here. And then we can go again coding time for SHAP. 3 collab codes here. Then we can, where my laser pointer, maybe this is good. Then we can go LIME, permutation, feature importance, MDI. I believe the couple of more, and then again a coding time. It is a very big coding, and you can do with me. Then I will explain you, and Subhash is also roaming around and come to you and see your performance, how you're doing. And don't mention or do the run all because it might crash. So that's one of the reasons. And everyone should be connected with the internet connection today. Okay, let's go for and real-time use case. I try to finish this presentation within half an hour. It's very difficult because you can go coding for half an hour, then again come back for the PowerPoint, go coding for half an hour, means again come back for that. We'll see that how that works. Maybe you can need a little bit of time. I don't want to make you hungry. I can stop at 12 o'clock if you want to talk with me again. After that, you can do that. Okay, this is a first our presentation, our project identifying patient characteristic for predicting mortality in patient with COVID-19 in South Florida. So what we did here, so it's an AI-driven decision support system, and to understand the most important feature, look at the most important feature, predict mortality. So we need accuracy. We need all machine performance of the machine predicting model. But most important feature, why you say that patient is susceptible to die. And anyway, so you see that black box. You might see, might not see before. The concept of black box is that you may not see the internal iteration. It is our duty. Means those are doing the data science work, but your audience may be doctor, nurses, clinician, frontline workers. They do not have much idea on the data science. So how you made them get afraid of coding and all those your mathematical intuition? So you make them as a black box. Is good for them. You send that 3 different kind of data set: patient characteristic, patient comorbidities, and patient medication history, and see the results. So this is the way we can approach the more details to the person's audience who doesn't have much idea on the data science, machine learning, engineering part, and maybe your stakeholder doesn't know that, doesn't want that. So this is one of the reasons actually we use the black box. So everyone knows that how you start our our work on the data science is a flow chart for you guys, the understanding the problem, these vital things, and because sometimes data is already collected, you do not have the any control on the data collection. Data already historically collected, previously collected, or you can say that retrospectively collected. So these data was collected, and you means they want to see that which patient are more susceptible to die when they have COVID. I'm sorry. Then you do the data pre-processing, data cleaning. This part is very challenging. You should have domain knowledge on this. Otherwise, you cannot do that. And then data analysis. I believe that 80% time a data scientist can spend in these two stages: data pre-processing and data cleaning, and then come to the data analysis, and then report the results. And when the data you report the results, means I could say the more data storytelling, you need to know that who are your audience, where you explain that those number, your 85% of accuracy, those things, or more visually presentation, you want to do that. So that will be more attractive or to the audience. How to do that? We can go mention a lot of things. I'm not going details of that. You see here, this is another flowchart. So in our case, that COVID-19 data was collected between 2021 and 2021, some month, I think March and January, and we see that 5,594 patients, and we also excluded those patients doesn't have the COVID-19. We confirmed that only 5,371 patients are COVID-19. Then we excluded those the columns, or you can say independent variables, are missing more than 10%. This is our criteria. Your criteria may be different. So our criteria is more parsimonious, so I believe that more strict criteria. So we just excluded those things, and then we got the 24 variables. And as usual, machine learning 80-20 or 70-30, you can split for training and testing or validation data set. So after that, it is a kind of very small. You do not need to read everything. So I could say the 3 different kind of data sets. Already I mentioned that patient characteristics, the age, sex, they're smoker or not, how many years they're smoking, and patient comorbidities like diabetes, diarrhea, those kind of things, and medication. So I have 2 medication in our data sets. So you might have more medication. And data looks like this. These are socio-demographic characteristics. Only I'm showing the 3 different independent variables. We have many. And you see the different colors that are segregating the patient are expired and patient are survived in between that. And this is the socio-demographic, the pre-hospital comorbidities, the cardiac arrhythmias, pneumonia, hypertension. We have many, diarrhea and kidney disease, and medication. So it is 2 different medication. And ARB and ACE, we use this medication for treating hypertension and cardiac problems. And when you see this data, you might feel that something means not usual. That's the different set of data expired are less and survived are more. You might call it means imbalanced data sets. As usual, any I would say the electronic health record is means imbalance. Medical data is imbalanced. So in that case, you first we split for the training, and everywhere you see that imbalanced data set. Means actual data, training data 80%, testing data, everywhere the imbalanced data set. We always balance the trained data set, otherwise we can get the biases when we run them in a model. I'm not going details, so this is not our topics today. How we oversampling? We use the SMOT. SMOT, but this is not our topics today. So, but you see that trained data set we already balanced, but test data we didn't do anything. So we ran the random forest classifier. This is one of the reasons we chose the random forest classifier, and because we have a continuous and categorical data sets, and for these, when you combination of continuous categorical random forest works better. And also our central aim is to see the important features that could contribute to the patient's outcome, that or the patient survived or patient died. But we do not do not maybe the secondary aim, how the model explainability, but you can get more details that later, that some model explainability doesn't taking care of this idea that your F1 score or AUC or precision recall higher or lower. Some is, some not. So we will go details. So obviously random forest classifier, I'm not going details how I do the hyperparameter tuning and all those things. Obviously this is not out of the scope today. But this is, you see that as you will perform the matrices, these are weighted average. Weighted average, you know that our test data is not balanced because real-time data set is obviously imbalanced. That's the reason we didn't do anything test data set, but we trained the model with a balanced data set using SMART. That helps to balance the data set. AUC is 76%, so this is 76%. It's a dotted line of stochasticity, it's a 50-50 chance. So anything beyond that means not beyond here. The patient means model is model learned, and obviously there's a lot of true negative to positive. Again, there's a false positive, false negative too, because it is not 100% accuracy. This model. I am going here. This is that after that, we want to know why model is robust and why model is, we explain model. So this is the things we are going to discuss today. So I'm just give you idea in real time, so it means, idea how we do that. But you see the two different methods used. One is random forest feature importance. That means idea means behind this we means how they did actually is a GINI importance, and this is SHAP analysis. Why you see two different color? Because it's a binary classification. So one is survived, this red is died or expired, and blue is survived. So is one. Yeah, so will survive. So this is the way, but this kind of, these are two different way, two different means method we used here. So why two different method used? Because the precision medicine, we should need to know whether our means feature analysis of means there any similarity or dissimilarity. If there is a dissimilarity, we have to take care of this. So this is one. I'm not going details here. We have a lot of scope to go details. So just I can give you the idea why, and we use that means the feature analysis. And this is kind of post hoc method, and as we use in statistics is a post hoc method. So after you run your machine here, you get the performance matrices, all your accuracy, F1 score, area under the curve. After that, you go to the feature analysis. So see that which feature important. If I go little details, so these are ranking order. So age is most important feature, and this is what is written here. So cardiovascular disease is the least important feature, and here age and obviously dependency of rate and dialysis is the least important feature. So you see the similar age, BMI, second important, race here not race, third important, diarrhea here third important, race. Then diabetes, diarrhea came fourth place, diarrhea came third place. So little bit of changing place. Most of the important feature are similar order, but they changing the place little bit of, means here maybe third, here maybe fourth, here maybe third, here other places fourth. So this way it happens. But if it is a huge change, obviously you have to take care of this. That's one of the reasons I want to see and want to run a different model. Okay. Any questions before starting actual presentation? Yes, please.
The data that you're assessing up here, did you do after the SMART?
After the SMART, we train the model, right? Absolutely. Yes, please. Okay, yes. Obviously, the different methods. We didn't do the neural network. because we use that two different methods is a model agnostic. Doesn't depend on the model, which model you work, means model agnostic. Some method is model dependent, so it changes. Some method is model agnostic. Our central aim is to see which features are more important. Okay, but obviously you can use a neural network. Why not? You can obviously should see that. And any other questions? And I can, model agnostic, what should I tell you? Yes, one more thing. This you see based on the trained data, not the test data. So you can check with the test data too, but why I use it on the trained data, because trained model, because I want to see the feature, the important feature, how our model are robust, how our model able to do that, means on the test data. But people generally do on the trained data, but I saw many people also, they did on the test data too. Okay? Okay, let's go here. So now I'm going to introduction. In this case, introduction to interpretability, already I explained that there are two kinds of model are used in a machine learning. When it is a black box model, we don't see details how the model works. This interpreter can provide cannot provide the transparency to the stakeholder. And you see here two different model. One is black box, you do not know what happens here. One is glass box. You see that what happening here. So two different, maybe when you use the glass box, you may not need feature analysis. So you already know that which logic you use here. So it's a glass box, is a black box. We go more, I believe that, yes. The objective that machine learning model optimize for do not always reflect the actual requirement of the means, the black box is kind of obscure, do not tell you what happenings there. And you want to evaluate evaluate the model decision, how model obtain the performance matrices. You do not know this, so this is kind of obscure, but it is that how that happens. So obviously I already mentioned this is a post hoc analysis, and after you getting your performance matrices, you do these things, and ensuring that the function of AI model is transparent, not solely relying on the complex algorithm, that lack of transparency. When you use you said the neural network more black box, more obscure, more complex algorithm, and it is very difficult even for you to understand if there is a lot of networks, lot of hidden node, lot of connections. It's very difficult to understand what happens. So you always need that model and model interpretability there. You see here when it is black box, if it is a neural network, or in our case, random forest classifier, you want to see two different things. One is accuracy, F1 score, area under the curve, and one is interpretability here. So there's a SHAP, LIME, MDI, and a lot of other things. So first is your performance matrices, accuracy, F1 score, you will see. Second is the model interpretability. Okay? So here you see more details. So you see that a glass box, you know the formula is a straight line, is straightforward, and you know the output, and what happens here you already know, and very simple model. And for the complex model, you do not need to know. You do not know that, but you need to know what happens. And if you believe your model, maybe your stakeholder doesn't believe your model. So for them also you need more explanation and what happens there. And also you see that two different terminology, interpretable machine learning, explainable machine learning. I could say that many of our presenters, Subhashit, I presented, kind of this presented many other conferences, their tutorial. Sometimes we means split it to different way, interpretable, model, explainable. But after searching and researching, we understand that there's not much different, or they are similar, same term. Many people got confused that interpretable and explainable may be different. They wrote even different articles, different way, but I believe there's more of them are same or similar. So do not need to worry of them, this terminology. You see here, the plot shows that trade-off between the interpretability and model versus predictive power. The model interpretability here x-axis and predictive power y-axis. We see the simple models such as simple regression models and classification here can be easily understand in how they make their decision, but their predictive power is very less. But the opposite way, we see we lost interpretability in a complex model, like the gentleman said, that neural networks here, so more accurate, maybe the accuracy higher, but less interpretable. We do not know because they are a more complex model. So you should do the trade-off between these two. So look at the decision tree, k nearest neighbor. They are trading off 50-50, maybe 40-60, 60-40 between the predictive power and model interpretability. So let's go types of interpretability. You see this chart, you can understand in general we can distinguish between the interpretability by design and post hoc interpretability. Interpreted by design means we trained inherently interpretable models such as using logistic regression, institute of a random forest, and post hoc interpretability means that we use the interpretability method after the model is trained. Post hoc interpretation method can be model agnostic, such as permutation feature importance. Here, model agnostic, permutation feature importance models. Model agnostic, such as permutation. Okay, yeah. A model specific also, such as analyzing feature learned by neural network, and particular model, that particular feature analysis method that use on the you use that ensemble model like a decision tree, XGBoost, or random forest, and some model you can use support vector machine, and same model you can use on the decision tree or maybe different. So this is a model specific and model agnostic, and also they explain model agnostic method explain two different way, local and global. I can give you the very simple idea. Local mean particular what happens particularly for patient number 201. What happens? We have 5,000 patients. This is what happened for the patient number 2001. I want to know why patient died. So what features influence on the decision making this patient is died? These are local. And the global, when you get the idea, means as a whole 5,000 patients, this is a global. So local is particular patient, particular, if I explain with healthcare data always, particular persons. But global is as a whole, all population. So that is the thing. So model agnostic, when you use this means, I'm explaining more on our next slide. ACE model can be used in support vector machine, maybe deep learning, maybe ensemble models, maybe k-nearest neighbor, but model specific, that particular this model using for that decision tree. That we are going to show before, we're going to see next slides. So now a little details here. You see that by design we can say the logistic regression, a linear model where the relationship between the input feature and output is very straightforward and easily visualized. So this is the things, and very much simple model. Maybe decision tree also be simple if you use a if then else condition and represent as the tree structure, making it easy to follow. Not all the decision tree is simple model. Random forest may be more complex. Maybe random forest is a summation of a lot of decision trees. So when you do the hyperparameter tuning and maybe you will make the model more complex. There's no more simple model if you do that way. So it is depends on the how you treat your model. So if it is simple or not simple. So after that, so you see that is a by design here, and after that, I'm sorry, after that you see the post hoc. Post hoc refers when you do not see the what model design, model is more complicated design, more complex design, then we can use that some post hoc technique that we already discussed before, SHAP, LIME, permutation feature importance, MDI. So those kind of things we use after model run, after getting the accuracy or performance matrices. So, and again, model specific and model means, agnostic. Model specific can be tree SAP, a particular tree SAP used for ensemble models. Also mean decrease impurity that used for the ensemble model. So those kind of MDI cannot be, you cannot use MDI in a support vector machine or k-nearest reasoning or deep learning too. And those kind of model are particularly used for means some predictive model. So these are model specific. So what is model agnostic then? So some model can be used in different of what machine learning model you can use. That's an example of kernel SAP, LIME, permutation feature importance. We go all details after that. You understand this, right? Okay. And now we come to the local and global. So here local and global. Local is LIME SAP. So okay, SAP. You see SAP here, you see SAP global. You might say, oh my God, you might be make it typos. No typos. Some means SAP also work. Local explainability, SAP also work global explainability. Local means particular, means instance. LIME and SAP both work. LIME is, I do not believe LIME work means global. Some means data scientists they use LIME for the global. We can show you, but LIME mainly used for the local. SAP used for both in the means force, when you use the force plot, waterfall plot, SAP used for the local, and when you use that partial dependence plot is used for global. And permutation feature importance only global. Some method only global, some method only local. LIME is only local. So these are the kind of means I'm not going details, but these are kind of means ideas why local method means needed. So local method explain the individual prediction. Local interpreter will raise the question: why did the model make specific decision for a particular instance or for a group of instance? Maybe you want to see the decision for the subpopulation. Maybe 500 people among the 5,000. So local interpreter cares little or not all about the structure of the model and is treated the black box model, understanding the distribution of data as feature space at a local level can give more accurate means what happens these particular people. And these are global provide the insight into the model's overall behavior, whole lot of data, means total amount of data, what happens, how the trend is. So trend is not better terminology maybe, but maybe yes, because when you see the different features as a whole for the population is means is obviously maybe trend. So but not maybe the means particular population, maybe different feature you get it. So it's a very if you want you can take the photo if you want, so I have no problem. So you see that couple of methods, maybe kernel SAP is global, local, both, and also yes, and some method is global and model agnostic and global, and but they don't have local means local behavior. They only have a global behavior, and feature these are global and model agnostic, and also some method is local. You see the local and but model agnostic. So it is, and some method is local, global, model, agnostic, all those means, characteristic there. So different methods has different interpretive characteristics. Okay, before going this, so I'm sending you our first email. Suppose you can come here.
Yeah. Sure.
Okay. Okay. Inbox draft, right? So which
Yeah,
one?
drafts.
Which one?
Drafts, explainable last one.
This one?
No, this is the part 2.
This one?
No, this is part 4. Go up. Part 2. No, go up. Again, yeah. Part 3. Yeah, this is the one.
This one?
Yeah.
So you are getting the email now.
Yes. Some of you might have.
So first email gone to you. So I'm now explaining the part you might now need to see. Is good now? Okay, good now. Good for now. Okay. So I'm now going to show you the glass box model. So this is the glass box model. So it is very, I'm sorry, if you do not see, it's a bit small, I'm not seeing anything here. So if you see, do not see, don't mention or don't feel any afraid of these things, because you will see these things before, you will do coding by your hand. So this is the idea, simple tree-based model, number of feature grows. So these are data for the, these are data for the flower, which kind of flower species, right? If anything wrong, suppose you tell me. So you see that some features, based on some feature, it is true and false. Suppose you please send them who doesn't have email address with us, who didn't register until day before yesterday, because we got the email day before yesterday who registered this the tutorial. So please contact with Subhashit, and Subhashit will send you the coding part. So yeah, so you see that the petal length is 2.45. If yes, it goes this way. If false, true goes this way, and false goes this way. And then you see the different way, based on the different criteria, the branches, everything. So this is a simple demonstration of how small decision tree is easily interpretable. You can easily visualize how decision is being made. A simple decision tree on iris dataset, right? You might know that iris dataset is a publicly available dataset. It easily produces the decision being made. Okay, the link you get on the email, just click the link and open your Colab with your Google account, and don't click the any code. We will do together. So you see the root. It is a root node. The model determines how the petal length is 2.45 or less. So it is classified patient. The flower is setosa. Otherwise, it move to other next internal node. Second speed based on the petal length. The decision criteria is whether the petal length is less than equal to the 4.75. And then split again based on the petal width. Petal width is less than or equal to 4.75. Then model consider to the petal, consider petal width and determine whether it's above the 1.65 centimeter or not. Past they determine the 4.75, then they determine 1.65. So get more bottlenecking and to get the decision actually. And then flower is virginica, or otherwise if it's not, then versicolor. So this way we split it based on the sepal length here, petal length, sepal length here, and we determine which flower it is. So if you see that, again, two different things. This is the interpretable model, glass box, and simple model. The simple model, you do not need to do anything, so you can understand very easily. And we do not use to any additional interpretable methods. I'm sorry. interpretability methods, and a glass box, yes, we have to do. So first we go to the simple method. So complex model visualize decision boundaries. You see that means, it is the some model has means I'm going to going to show here that decision boundary of different model. So some model has like ensemble model visualize and also better comprehend weights assigned to each base model within the ensemble. Typically, base model have a strong influence in some region of the feature space and little influence of the other. However, there might be a base also be base model that never contribute significantly to the ensemble output. So I'm identifying base model with the particular low or high weight can also help. That if it is a high weight, so that means it's important, or it's a light weight, means less weight, this is less important. So different colors showing the different darker areas, slightly higher confidence in prediction, but lighter area represent the lower confidence in prediction. So less weight on the lighter area, but these are different way, different logic you can use. These all are glass box phenomena, so you do not need to do anything. You see that techniques, model A, B, and C, the technique, same technique. Maybe if this is the model A support vector machine, this is decision tree, this is maybe deep learning, and same technique can interpret. And here, this is a model agnostic. I'm sorry, this thing is not working. This is a model agnostic, and this is not the model agnostic. It's a specific technique is needed. Okay, so there are a lot of model-based interpretability. Until before that, we used model. Simple model means simple model, glass box. Now we are coming the black box. So black box model interpretive technique, it is model based decision tree, linear regression, logistic generalized linear model, MDI, mean decrease in impurity, Bayesian. We are not discussing Bayesian today. And also model agnostic and SHAP, Lime, permuted feature importance. So similar to SHAP. So we will go all details after that. So model agnostic, explainability, partial dependence, Morris sensitivity, individual. We discuss also those method. Okay, let's go for coding. There's two coding. First, I sent you iris data set. Then we can come for the breast cancer data set. So let's go for that. You're seeing this thing now? No. What happens? Okay. Maybe this reason. This is good, right? Okay. Shubhata, did you send everyone? Yes, please. Collab. I can wait for you maybe a couple of minutes. Would you see that we can get the same screen on your computer? If it is not, ask Subhoshit. So can I start? Okay, let's go for that. So every other data science project, you have to import libraries. So you click on that. So that's imported your libraries. Hope it will take little time. Then import your libraries. Don't run all. Don't click these things. It is showing here. Yeah. Don't click these things. So it might crash. So go one by one. Then you see here already we discussed before that these data sets hold 150 sample of 4 attribution flower. So 4 different output of the flower. So flower is which kind of flower? Cytosa, virginica, versicolor, I'm sorry. I'm little bit telling differently. 4 attributes is independent variables, whether based on the sepal length centimeter, sepal width centimeter, petal length means length, petal width length. Based on these 4 features, we try to understand which flower it is. Either it's Citesoa, Virginica, or versicolor. So we based on this 4 feature. This is the ID, and yeah. So now you load the data sets with me. So you know that how means these are public data sets. So if I first split that x is 4 different attributes, and y is a target, like either which particular species. So and also that it means in any before running machine learning, and this was the CSV files, and we uploaded and made changes in data frame. Otherwise, you cannot work on that. So you need to do the data frame. Then we'll see that it was the 3 different species we already made. I already mentioned before, and we changed the dummy coding. Maybe cities or 0, versicolor 1, and Virginica 2. I didn't use the one-hot encoding because more understanding. Maybe one-hot encoding reduce the biases. This is not. But anyway, for today's class, we do the dummy coding this way: 0, 1, and 2, and see the 0, 1, and 2 all data sets. That's truncated anyway. They are not showing the full data set. It's a truncated. Otherwise, you want the full data set, they can do that. And then they see the distribution plot, and we see how the features are distributed. Look at that 3 different length based on the 3 different petal length. How the 3 different flower species are distributed, and petal width and sepal length, sepal width. Everyone doing that right with me, right? Everyone doing that? It's good? Good? Very good. So if anyone stuck, let Subhush, Dr. Ray know there's a different, you stuck it. And then random forest classifier, I use a random forest classifier. You can use something else. So we use a random forest classifier, and random forest classifier model feed, X train, Y train, this way. And then go to the results. So see that confusion matrices. So in this case, you might get surprised. What you get surprised? Look at the accuracy is 100%. So you might get surprised this. So there are a lot of reasons. So maybe the means less amount of data. Maybe you need the more amount of data. But I made it willingly. Means accuracy is 100% because of the reason why. We'll see that what happens when the accuracy is 100%. So. And then area under the curve. What will be the area under the curve when the accuracy is 100%? Maybe 100% too. See the 100% area under the curve. So here all accuracy peak accuracy F1 score AUC 1, and its AUC is plotted, is also 100%. And when there is 3 different outcome, so you can plot that AUC to 2 different way: 1 versus 1 and 1 versus raised. And 1 versus 1 means what is the difference between sepal and petal? These are 1 versus 1. What is the difference between sepal and rest of the features? 1 versus raised. So this I made the coding for you, and I think it's 1 versus 1 only there, or here 1 versus raised maybe. Here 1 versus raised. So this coding is very important. So 1 versus raised means one group versus all other groups. So this is 1 versus raised. One group versus other group, other particular group. Maybe there is a 1, 2, 3, 4 groups. So when is 1 versus 2, this is 1 versus a 1. This is 1 versus 2, 3, 4. This is called 1 versus raised. Okay, is it clear? Understand? Okay, good. So after that, this done, this done, this done. Good. So plot, and now we see that tree. So we'll see that what happens here. So okay, now you see clear diagram, same as before. You see here, petal length is 0.7 less than equal to These are criteria, and then we true, if it's true, it goes here, and class is Citosa, and false goes here. And when you see the GINI is 0, means that this is the absolute class. We cannot means classify more. In my presentation, I just noticed that somewhere GINI is 0, then the classifier, I have to check on these things. But when GINI is 0, we cannot classify. And then if false, the petal length is different, means not more less than equal to 0.7. We can see here, and means it is more than 0.7. See the 1.55, and also we, based on this criteria, we can split it and split it more until your GINI is 0. But here still GINI is there, they didn't split anyway. So until GINI. So and also remember that it's a root node, it's called root node, and it's called leaf node, and leaf node is down here, leaf node, and what means features are near to root, they are more important feature because of the more weight. Okay, so that's done. We actually used two different library functions to show you guys that how we can make it possible. And this is the a little different way you can do that. Petal length 0.7, it's the same things, and we different way we split. I already explained all those things. When you go back at home, you can read it. If you didn't understand anything, you can just email me. We can talk each other. So now we can do that, and don't run 2-3 cells together, run one by one, and then we'll see what happens here. It is a little small diagram, it's little smaller. So a little smaller, with you can you can zoom and you can see that how I differentiate three. It is another way. Means we can see that random forest is obviously descent classification, how we did the descent classification. So okay, and Shubhajit, can you come and see? So you are getting now the second email. Where it is? Come.
No, this is the backwards. This is the one.
This one?
Yeah.
You are getting the second email. Come here, class box 2 here. Well, I can open both, I can close this. If you want, you can close the other one. Oh, sorry. This is the one? Okay. So these are different kind of data. Okay, I can give you one more time, a minute, maybe 2 more minutes, so we can set up all those things. Everyone got it? Shoes, can you roam around? You'll see that how they work. Okay, same way you can installing the libraries. I'm explaining the data after that. Install the libraries. This is a little more data sets. So this data set 198 samples, 80 features. The other one is 4 features. The 80 features, the endpoint of the presence of distance metastasis is the breast cancer data sets, and which occurred 51 patients, 25.8%. And they did actually try to understand whether malignant or benign. Malignant cancerous, benign is not. And the features are computed from the digitized image of fine needles aspirate, FNA, breast mass. And okay, so if you want to read more, you can go to this citations and you can read more how they did. So let's go and do that. So now we are uploading data sets, then splitting the data sets train by train, and then you go fit your model. I use this time decision tree. This is the a part of the ensemble model, not very difficult with the random forest similarity, obviously there. Then it is the prediction. You see how prediction 91% F1 score is F1 score. What is both are 91%. Good. So we'll see the AUC here, but this is not 100% is this time. We'll see how the AUC. Okay, nice. If we see here 92% here. So AUC. Obviously, you can check before that, before running anything. These are basic things. And now we see the feature importance. I am not going details here at this point. We are going to, this is the feature importance using the MDI, mean decreasing pressure. So which I'm right? So this, you see that this is the not means glass box. I want to just compare with the glass box and what to say, the black box. So this we use for the black box. It's a little difficult model. That's the reason I just put that things. So this is not our time to discuss this. We'll have later we can discuss. So mean concave points, Oates area. These are most important features. See that how length of the bar is. This length of the bar can tell you how much important. That's the reason it is the first place. And next, Oates area, next. This is the least important feature is a mean texture. So, okay, until this, okay, good. So this is no need for you because we use a dummy coding and they change everything that way. And now we see the visualization part of the trees, how the trees looks like. You see the trees here. Oh my gosh, it's a huge thing. Show different criteria based on the different criteria. They splitted the trees. There's a lot of trees. Means a lot of decisions they truncated because trees goes means beyond the length is a very bigger. And another way we visualize. So this is your asset. All coding you got because we tried hard to find this kind of coding for you guys. This is not truncated. Look at that. That gives you the full tree, not the before one. Subhashit, someone asking question. Someone asking question. So yes. So this is how big a tree. So this gives you the full tree. Everyone get this part, right? Everyone get this part? Okay, good. So now this is the thing. So I could say this is the end of our glass box. Now we can go to our black box now. Okay, are you ready? Good. Do you want any break for 2 minutes? Is good now? What time now? 11:56 is good if you get the 4 minutes break. Good. Any coffee, tea? I know I'm little bit of faster because we have to complete this. I'm sorry for that, and all codes are with you, so no worries. Okay.
this one, part 2, black box 3. Because this was the, I think you just sent me,
I think in part saying but we'll come to that later on.
oh, okay.
But it's not working too?
So when alright, so this one, alright, so part 1, glass box 1.
Yeah, we did.
Yeah, so we did that. I had to manually change, these are some characters that were causing the error, and then I could upload it.
Okay.
But then when I did it for this one, there's so many errors that I couldn't actually upload this. So can I get this?
Yeah.
I've been having the same issue. They're like invalid characters.
Yeah.
Wow.
Okay. Give me a minute.
Sure.
You mean the black box too?
That in what? Yeah, same file. Oh yeah,
Just this one? Okay.
This
it's not showing up in my Google Drive.
Oh, all right, so this one.
Okay.
Yeah, same with
All right,
Word.
so this, all right, so I guess he sent out the wrong.
Okay.
I guess he sent out the wrong.
Yeah.
Okay, fine. Thank you.
So yeah, and if the multiple regression doesn't work, we'll see. So tell me your
Mr. Rock, MR period.
I should have
Yeah, it's the one that's highlighted.
Cool.
Thanks.
Computer box to open and we should have it.
So what's the next file?
Next file is going to be SHAP interpretable. We haven't sent out yet. Yeah. Yeah, sure.
I'm still getting invalid character error.
For the new file,
Yeah.
it's something there.
Yes, it's invalid. Invalid character Jason.
That's interesting.
Yeah, if you just search it. I guess if I did.
There is another way I can send it to you is by going here and click share and place it and send. How about now? I send you. Email that shares to the file.
Yeah. Oh. Yeah, that's.
All right.
Very good. Thank you for troubleshooting. See that how the people. I'll call you when I send to them. Okay, I'll call you.
The SHAP regression also got sent out, mistaken.
Regression center.
Yeah, regression also they have.
Okay, okay,
Sure,
okay,
sure.
okay, no problem.
We'll send it again.
Okay, we'll send again. So do that. Okay, let's roll. So first is different interpretive methods and both are all are post hoc. Let's go for the SHAP analysis. I like SHAP very much, and I use our 2 publications SHAP, and also you can understand why I like SHAP, and you start liking SHAP, and like SHAP is more powerful model. Still subprime models, more specific, sometime local, sometime global. All characteristics are there. So Anyway, suppose you told that you got a SAP link, but you don't click the link right now. Keep it with you. We can go means one by one. So let's go. So SAP means Shapley additive explanation, and this gentleman, okay, wait a minute. This gentleman called Lloyd Shapley, who got the Nobel Prize on in economics 2012, and who made this model, explainable model, and based on the game theory, cooperative game theory. I'm not telling the game theory here. Our goal is to make this session more interactive. Instead of explaining the hardcore math. And I like visualization part, so you see lots of visualization after that. Less writings, less words, but a lot of visualization. So let's go and see that this is an example to build the intuition for SAP. Suppose a company wants to divide the annual bonus among the workers based on the individual performance. How would the company go about it? SAP was primarily used to situations like this. Still, it has been further developed to be utilized this way. So model feature based on the experience, degree, sales, performances, and days late. Those data is either continuous or categorical, category binary here, all are continuous except this degree. So yes or no maybe. Which features are most contributing factors to the model outcome? Okay. So we see that you can, it is the features, independent variables, a model, and give that values. What is this value mean? So what is this about? Let's go. So SAP value, maybe I can go here. As you can see that model's output is 0.9. The SAP analysis that identifies which features contributed to the model's output. This is the individual features contribute. When you add up those individual feature contribute and get the 0.9, and which is given by the right columns here. So here. So if you add the individual feature, you can get this value. Okay, let's go there. So now individual feature contribution, and then you can add up and you can get this value. So 0.9. What about this value? This SAP value is computed, but that perturbing input feature by seeing how changes to the model. You see that the values are different. Some is 30%, some is 10%, some is 20%. What is this 20%? So maybe 30% is more important, and maybe 20% less important, 10% of less. 0 doesn't have an influence on the model. Even you can delete these features, you can get the same 0.09 values. So that doesn't influence to this model. Okay, so we'll inspect the mathematics, how this being derived in the next slide. The idea is how each feature contributes to the model. This is an indifferent subset of the features and summing over. And it means, what to say? Okay. A value of group with a player as a member minus the value of group without the player. So we compare those kind of things. The member, maybe 5 members in a, I can go later, maybe you can see here. We can see here. 3 members in a group, A, B, C. We see when 3 members present in the group, how the model output, how the model performance. We delete 1, A, C, B and C, how the model performance. Then we delete B. We have 2 more features, A and C. We'll see how the model performance. Then again A and B, how the model performance is. So this way we can do the model performance. We compare this and then understand which features contributing more to the model. You understand, right? Okay. Now, this is a part, if you like or don't like, I just give you a little idea. Here it shows the SAP features, how passive feature calculated. We identify model output with and without features I for all subset, this A is all subset. We calculate difference of model output with and without feature I for all subset and average it. out of average it and see that how the model performance is. The average gives you the SAP value of contributing particular features I, that maybe age or diarrhea or diabetes, so those kind of things. So after that, considering particular order coalition, we need to weight the marginal contribution according to the number ordered sets if possible. This is given by, as shown, the weight for all subset. The value is here, the varies from 0 to n minus 1. N is total number of the features. N is the total number of features. Okay, good. So here we see that marginal contribution y for a given coalition of set A is and we two groups S and total n, and we see the ith instance, and these are the n minus s minus 1. So yes. Okay, anything Subhajit want to add? Very quick.
Yeah, so this is showing you. So yeah, this is showing you for each coalition, which is S. Now, if you add the ith feature or the independent variable to that coalition, what is the improvement it's making? So PSUI is the minus PS is giving you the boost. And then the whole permutation term is like you can arrange S in S factorial ways. So you see that S factorial term over there. And then the remaining of the coalition you can arrange by n minus s minus 1. So that whole component is like a probability picking up that component. So you're just weighting that boost for that particular coalition by that probability. So if that made sense, okay? Yeah.
Okay, let's move. So you see here, I'm not discussing the surrogate model. Shubhajit, do you have a slide with surrogate model, so we can discuss later. So you see the model F is the original model that you maybe use a random forest or decent tree or means what you want. And model G is the explainable model, that's SAP. And then you train the send the train data sets. So you can send a stage data set too, but I'm very much inclined to the train data set, see the actual model performance. So this is the way it happens. So we'll tell you later the concept of surrogate model when Subhajit will present. And there's a different pip install SAP and the exclamation marks before pip when you install SAP on your Colab, you do that. And then explanation model, okay, I already mentioned you that model specific sometime, tree model used for XGB boost or decent tree or is model specific. So deep explainer for neural network, this gentleman already mentioned before, then why not neural network? And linear explanation means explainer regression model. So see that model specific, but obviously you can use also some model. We're going to see that. Kernel explainer for the model agnostic, right? So yes. So yeah, you will see that there is the advantage, disadvantage. Advantage model agnostic, that way you can model specific, we can use also is a kernel SAP, this okay. Model agnostic, model specific, and also SAP could do the individual prediction, local and global, whole data sets. So all characteristics are present. Let's move and see that how that happens. So this is little bit of ideas and means if you do not like the mathematics, so different way we can make these things possible. So you see that the problem is we expect the housing price to the based on the features such as the location, lat long, incomes, total rooms in the house, and proximity to the ocean. So more proximity, more near to the ocean, more price. And we'll see that x-axis that gives you the median house price, and y-axis give you the median income. The one feature only I took. One features, the independent variables, and the dependent variables here, the outcome variable, or we can say other words, housing price here, and the vertical line, this vertical line give you the dotted vertical represent the average value of the median income. So yes, And here we are showing feature income. This is a particular 20th instance, mean the persons, the 20th persons who actually bought the house. There's a lot of other persons. So x-axis already I told you the median income here, and y-axis shown the expected value of the housing price for a given median income. A particular dependency, this is a partial dependence plot as shown. This gives the relation as average effect of single features. Median income, the single feature, we only plotted with a single feature. There's a lot of other features there, but only plotted single feature, make it simplicity. And on the predicted outcomes, this is a predicted outcome, marginalizing all other, we rid off all other features, that lat long, proximity to the ocean, we rid off all those things. And after that, so SHAP has two values. One is base value, another one is SHAP value. So base value is the expectation of housing price is average over all instances. So this is the base value, dotted line. It's the base value. Number of instances are 2,000 housing price. This value is constant. Even if you want to check the particular instance, this value always be constant for all particular features. We didn't calculate all features. So particular features we have to count constant. Even when you check the global, means not particular. If you check the together all other features, maybe that time also this line is constant for overall model prediction. So this is called the base value. So we can write this way, EFX. So these are base values of this. And SHAP value for the 20th feature, this amount. So this is the 20th feature, how that changes from the base value. So these are SHAP values. And here you can see here 20 expected model output for the 20th particular these persons, and this is a base value. How difference is this? The difference will give you the amount of SHAP values. Okay. So this is, I try to little artistic for this presentation. So SHAP linearity experience. If you add up SHAP value for every features with the base value, we end up with the resultant SHAP value of the actual prediction for the particular instances. So every other feature, so we already been checked for the income. Maybe we have a lat long, proximity, other features. So all feature for the all different feature, you can get the different SHAP values, and we add up, we can get the means actual prediction for the particular instance. It's a local. Okay, you can make it global too. Let's go and see that different SHAP plots. So for regression model, the base value is equal to the mean of the target variables, mean house price of in the data, whereas classification model, the base value equal to the prevalence of the positive plus. So the classification model, what happens? 0 and 1. So binary classification. 1 is died, 0 is survived. So in that case, it should be 1, the base value. But the regression, this is a regression plot. It's depend on how I showed you before, how the things was calculated. So if you see that this is the base value here, and this is these are SHAP values of this particular features. These are local methods. So SHAP value here. So least important feature this start from the base value goes little bit negative, and where it ends, next feature goes from there to little bit positive. Where it ends goes more positive. Where it ends, next feature goes more goes negative, more negative, more negative, more negative, more negative. More negative than more positive. So remember that this, always we use the SHAP values, the absolute value. Which means for the local plot you use that positive negative means the positive negative. Sometimes you use only the effect we calculate, we do not care the positive or negative. We know that's positive or negative, but when we see that which feature more important, this feature also important because this is negatively influenced. This feature obviously important, positively influenced. So this is the way how SAP give you nice plot because the length of the plot gives you the impact to the model, how the importance of the features. So go next. This is written same explanation. The feature of each contributing push the model output from the base value, push the model output from the base value to the model output. Feature pushing prediction higher are shown in red. Those pushing prediction lower are shown in blue. Okay, there's another way we can do that. So remember that if you take the photo also good, but this means we go for the real time coding, but the things like that sometimes they change the library functions. We might this code might not need sometimes we have to search for that. So another way to visualize this is called a force plot. It's individual instance prediction. You see here this is a base value. And this indicates the values that are going to be higher values to the function. This indicates the lower value function. This length give you the which feature more important. This values is actually SAP values. So base value for the it gives you the output function for the instances. This is a base value plus SAP values. So look at the length here, more length than other in comparison to the other features. The contributing particular feature from which you can identify most important feature here, more important feature. So okay, so I do not know how do you explain, how do you say that is a local or global. We took 500 instances, not whole lot of, not individual instance. We took the 500 instances. This is a force plot though, but such the way we rotate them 90 degree and we stack them horizontally, we can see the explanation for an entire data set. From the population plot, we can identify instances where positive features values dominate and red are positive are dominate. Here instances we see the positive dominate and red are positive values always. It's kind of heat map. So all cool color goes to the lower values and hot color goes to the higher values. So if we normalize 0 to 1 scale, so 0 goes to the the blue, and we identify instances where the negative features dominated here, negative features dominated, and positive were less dominated. So I'm not going all the same things here. So in the force plot, population instance can be ordered based on similarity. There's a drop down menu. We can change that different way: married, less educated, married, well educated, large capital loss, middle-aged, educated, single. So those way we change the different sub features and see how plot looks like. And this is very important. These instances can also be ordered based on the model output and plotted in a descending order. See the more positive here, less positive here, more negative here. So descending order. And also here, this is a different way. Those are the force plot, and these are the different. So SAP decision plot. In the decision plot, each line indicates the instance and change the decision starting from the base value. Starting from the base value here, and this is the final model prediction. And each observation's prediction is represented by a colored line. At the top of the plot, each line strikes the x-axis top, not bottom, and its bottom is a base value, and corresponding the observation predicted value. This value determines the color of the line on the spectrum moving from the bottom to the plot top. SAP value for each feature are added model base value. This shows how feature contribute to the overall prediction. So now tell me the base value is positive or negative. So here 0, here you'll see the base value here. So base value is negative, right? Good. Let's go here. So now we normalize. Here you see that negative and positive, all those things. So I don't like negative. So let's normalize. Normalize give you more comparison, means better intuition of the comparison, because all are same side. So more changes. You can see the normalize is 0 to 1, and it is a dotted line, is the overall prediction of the SAP. Oh, you can find the overall SAP for misclassified. We can go for the misclassification later. So there are most important features, less important feature, and those goes beyond this less distance from here, 0 to 1. So more important feature than this way. So negative also important, sorry, blue also important, negative also important. They influence negatively, so they supporting more survive class, and positive maybe they support from the person who died. Okay, let's go here. So here is a hypothetical scenario, understanding of where the model would give you the erroneous results under unnatural situation. For example, we created hypothetical values here. We change the value. Then we calculate a SAP value for the new range values for capital gains. Look at the capital gain is very much down, bottom. And we can plot that, see how the more model will, when we change the range, we see it is still in bottom. I don't know why it is bottom, but it impact is, you see that impact is high. So it goes here. It should be goes nearly 0. At the bottom, we can see the capital gain contribute almost very low in decision. However, under hypothetical value with the range, we change the range here of the capital gains, they become one of the major contributing factors in the model decision. It is obviously erroneous. Some problem happens. That's the reason. So, and also, when you see that there's a 4 different classes, now binary. This is not a binary. These are 4 different classes. When the 4 different classes, each individual classes we plotted here. Outcome variables. Remember, they're not input. These are the independent variables or features. This line in this class are outcome multi-class decision plot. So see that how many are there? 0, 1, 2, 3, 4, 5, and all individual class prediction. How this feature changes individual classes. So we just wanted to see this and see here that a couple of classes are very close. You cannot distinguish between the class 3, 4, and 5. They already same or very closely values, and these are the different values, and you can distinguish very easily. And now here, how we want to see that, how global versus local of the same data, same kind of plot, SAP bar plot. We can see just as mean absolute is the mean absolute values. So you cannot see here. It looks like how SAP values all are absolute values. So we do not see the positive. We do not means you cannot get idea which values are positive, which are negative. All are SAP absolute. Here the same plot we can plot, means same data we can plot it, and you see that what the negative and positive. So SAP we can use for the global and local both in this way. How nice it is, right? So now, okay, now here we change a little bit. Here we see the age. Maybe age we could give the criteria of less than 70 years, more than 70 years. So it's subgroups. When it's subgroups and gives you 2 different plots. And here men and women, or here men and women where gender, right? Where it is men and women. Oh, I'm sorry. So this is actually we divided men and women for each attributes. So there's a 2 different group, 2 different sex here. So those are independent variables. So men and women, we wanted to see how the distribution of men and women, how the SAP value changes for the men and women. So you see here, I think very close, dotted line is women and dotted women and continuous is men. So we changes. We need to know that subgroup. Here you see the code that 6 data 0 0 and we means and when 1 is men and women. Okay, let's go little. Oh, why not? Why it is same? Okay, I'm sorry. Okay. Oh, nice. Okay, nice. Oh, we already, it is the repetition. Okay, anyway. So now, we try, we are a little more adventurous at this point. So this is called the SHAP B-SWAM plot. In this plot, we want to see the local and global and both together, absolutely. So you see that the different, here is a better way, so this is a better way. So we see that to get overview which features are most important, obviously same way they are given, and the model also we can plot the SHAP value. Every features are every means samples. The plot here shows that feature by some of the sample magnitude of overall samples. They're giving you overall sample and distribution. That's the important word I'm just trying to find. The distribution of the individual instances, how distribution looks like, right? So distribution looks like. So that gives you the both local and global. And this is called the B-SWAM plot. I like this plot very much. Every my publication I try to use this. So this is a different way you can use that. You just see that we can change the SHAP plot violins, SHAP values. It is a violin plot, right? To different, that means it's also B-SWAM plot, but I'm sorry, with heat map. It's a two different way you can plot the same plot. This plot actually this plot. So this is we call the SHAP dot plot, the B-SWAM and SHAP values. And here we change a little bit of this thing. We added little violin here, violin, and then a layered violin. Oh, it is a layered violin plot type. I never used this layered violin before. So layered violin. So yeah, this way do that. Anyway. This is again the interesting things. So you can plot both side by side. Both are. This gives you the global, and this also gives you the local. It's not all local and global. How that looks like. I believe that in this case give you more information than this. So if you plot this, you do not need to plot this. You can write down you explain your plots. Better way here and give all information that you can give here also. So you don't need to plot both. You may need only one plot sufficient to gives your project to the audience better explanation. Okay, little bit of different thing now. So it's called a SHAP heat map. So SHAP heat map can be useful understanding the relationship and cluster. There's a native hierarchical clustering that heat map deploys. However, we can improve in this way, different way you can improve. Similar features here, more important here, less important here. The positive, negative, how all red are positive and the negative, how they impacted on the model. This all means this is the instances in this case. Remember the instances, not the SHAP values. Here the overall features, how you added the instance 0, instance 20, 200, 400, 600, 800, and how the overall prediction gives gives you the idea. Prediction higher here, lower here, maybe a little more higher here. So this way the prediction goes. So model output, this case is very much clearly shown you. Model output and the instances and the SHAP bar plot. Okay, the SHAP bar plot. So gives you resultant of the positive, negative. That means SHAP bar plot is higher means more important features. You see the more important feature than lower. So yes, and horizontal lines indicate the higher or lower prediction. This higher low. Red and blues that shows you the low. Red shows the high and blue shows the low values. Now we are more adventurous here. So sorting based on the prediction. You see that here we sorted based on the prediction. So we wanted to know that when prediction low and goes to higher. We do not want to make the prediction drop here again. We started lower prediction and want to go higher prediction. And based on this logic, we arrange the features. So sorting feature based on the prediction. So this way we do that. And here we are more advanced, sorting according to the most important features value, most important based on the cell weight. This is the features. So based on the feature, is here outsort cell weight, and what was there before is before a Y prediction outsort same coding. We change the coding difference, means our criteria based on the most important feature cell weight. We arrange this, and that reason means it is means lower higher zigzag means it happens because if you see here it is kind of means continuous blue then red. Obviously here in between some red in here also in between. There's a reason based on this we get it. So it is not means as before we get the low to high. It is some zigzag is there, some ups and downs. Okay, so this is the scatter plot and based on the how the particular model working class. This is a model. This is SHAP values, and these are SHAP values, and these are instances how they are distributed. So these are number of rooms how they are distributed. That's the same data sets that we already mentioned before, and that is the some features. So you have to read those things. So roommates, how many roommates depend on the SHAP value got changes is kind of distribution of the single features. Now we see that we can plot these things. So how nice it is! It is more interesting. I can mention going to more adventurous things that SHAP can give you, and maybe whole lot of presentation we cannot see again. And those kind of things. I'm coming very soon. So this is the age, only one features, and the SHAP value how they're distributed, and this is the age. I believe that what we changes. Suppose can you see that scatter plot age? Education. Oh yes. Oh yeah. So this is right. So this is the actual age and education numbers. So this is an interaction plot. So these axes give you one features, and this gives you the another features. So how interaction happens, how two features interacted to the model. One of our publication we showed that interaction. And remember that that's only SHAP can give you this idea. I didn't get any other thing. If you get it, email me that hey Deborah, so that some other way we can get this interaction. Look at that here. So systolic blood pressure and age, how that distributed. This is the lower age, it is higher age, and systolic blood pressure is less for the lower age, high for the higher age. So this is the age and sex, and this is a crossing over happens here, and age and sex. So how the means in the data. So age is less here, and sex is female here. Starting with that, then it goes here down, and this goes higher. This started with a low value and goes higher, and meet here. So how nice it looks like. We are means end of the SHAP. Any questions you have, I'm sending you the code, then we can do again those kind of things. Okay? Any question, please? So, first one is black box model, not this one, right?
Not this one.
This one?
Yeah.
Now you are getting one email, and please open this and the black box app. Whatever. Oh, this one, right? If you get this one, let me know. We can start after that. Okay, let's go. So understanding SAP. So we have 3 different coding exercise. So of SAP, SAP is very big. So that's the reason. And don't run all, don't click there. We can get a crash everything. So you click this is also dependency. We can come to the data. So then we wait until this run fully. So don't click both, means two different cells together at the same time. Okay. Any questions you have? Suppose can you roam around and see, please, if anyone has any help, need any help. So I'm this second cell 1.2 downloaded the data sets. So you got data set downloaded, right? So now we pre-processing convert the data to the pandas data frame that I mentioned before. This converting data to the pandas data frame, and this is the okay. I cut the data set. It's lots of. I don't want to crash it for again and again. So only 2,000 data instances I want to make this today's exercise. So do not need to do. You can do that at your home. So you just delete this line. You can get that whole data set. Don't do that now. So you cannot get these things. So now you see the looks like data, how the data looks like. So look at the data. So a lot of variables are age, work class, I don't know, fun, late, education number, marital status. And we want to see here income, the less than or more than 50K. So this is our dependent variables. Look at that here. I already put these things to explanation, to give you the explanation, the data. So age, capital gain, capital loss, all those all are independent variables except the last one, work, no, except this is rated in there. Income, where is income? Where is income? Maybe I wrote it somewhere, income. Here. I wrote it. That's the reason. It is not there here. So dependent variable income, whether this person's income more than 50K or less than equal to 50K. So this is binary. Yes, binary variables. We make it binary because of the 2 different criteria. So now we see the target distribution. How the target distribution look like. So click this 1.3. Look, see that this is also. What is this? What is the problem here? So these are dependent variables. Anyone can tell me that what's the problem here? The income. If you get this graph bar plot, what's the problem here? Anyone can tell me? What do you see here? What's the problem here? What do you do here? Anyone? Imbalanced data set. Okay, nice, Subhajit. So imbalanced data sets. So imbalanced. I'm not doing anything here because this is not our class. So to balance it, you obviously have to balance it. See that, like before I showed you that this class, this is a minority class, less data present here. This is a majority class, more data present here. But I'm not doing anything here at this point because it takes time. So a couple of coding are there. If there's a NaN values, there's no NaN values. If there's a NaN value, how to drop the NaN values. So I already, don't run this. Do not need to run this because this already commented. So if you run this, nothing happens. So you can use this code when you have these NaN values. Generally means data has a lot of NaN values. So that's the reason actually I put it that. Okay, that's a 3 different groups, types of data: categorical, numerical. Numerical is continuous. You can change the name, con maybe better. So num and time data sets. So they gives you 3 different data, age, and these are numerical data sets. The continuous, age obviously continuous, capital loss, hours per week. And this work class income is our dependent variable. There's a categorical, less than 50 or more than 50, means less than equal to 50 or more than 50. And these are time features. So time is a 3 different data, separate kind of data. Data structure. So that's the reason. So now I want to see that the categorical variables. And when you do this study, any project, please understand the data much. Don't blindly use machine learning model. Please understand the data Means otherwise you cannot explain the result. Machine learning cannot explain you decide which machine learning work based on the data sets, how you're understanding on the data. So obviously y is target variables. What is the target variables? The income, right? The target variables. So it's outcome variables. And except this thing, we drop income here and make the data sets. All are independent variables or features, what I would say. Now here we use random forest here. I like random forest much. Anyway, because we use random forest, there's a lot of continuous and categorical data set together, and random forest give you the robust result. But you can change compare different machine learning model and see how that changes happen. And next, I do not need to use that concat, it's already concat. So you see the results. Oh my God! So all I told you before, there's 0 and 1, and there are binary outcomes, and you want to see that all those things. We come to the classical matrix. Subhoshit and I made this thing possible for you to make all tutorials here, and you go to the code. Actually, you get all ideas. How that means how correlate the results, how you explain the result, everything. This is a confusion matrix, and this is the idea how confusion matrix happens. So this is a confusion matrix. So 0 and 0 means true negative, 1 and 1 true positive, and except all this falsely classified. And this will give you either type 1, type 2 error, and prediction quality matrices, and true positive or true negative, all that here. Balance accuracy is very much important when you have imbalanced data sets. In this case, the balance accuracy, I want to rely more here than here accuracy here. So here more, and F1 score also. See that how different things happen. So accuracy, you see the accuracy here. And the accuracy 83% of balance less. Because why balance less? Because the class is imbalanced. So that's the reason balance is less. And next, give you Y test prediction and precision recall, all those things. So yeah. And this is obvious. I hope that you understand everything. So it is the very primary criteria you need to know in order to understand the feature analysis. So if I describe all those things, it will be out of the scope and also the time consuming. So I only go for the feature portion. And there is a random forest classifier for the one. This is the trained data sets. This is a trained data set. The data already machine is exposed. Is a test data set. Machine never exposed before. So this is the reason 1 and 0.9. But anyway, it's a better things. Oh, Shubhoshit put this thing again. Okay, that's great. So you get all formulas here. When you go home, you can again run and see that. And the lots of different way you can find. You see that I segregated this thing, training set matrices, test set matrices. So even the R square value, mean accuracy, what is the ME, mean error, mean absolute error, absolutely. So then a SHAP, also how SHAP works already I will describe. And now you import SHAP, and you click and wait. So don't click two cells together, please. And now you initializing tree explainer. Why you use the tree explainer? Why we use the tree explainer? And tell me why we use the tree explainer. And why even it is model specific or model agnostic. How your ideas? Why use a tree explainer? Anyone can tell me? You can volunteer. Can tell me anyone. So tree explainer because it is a model specific and because we use a random forest. So that's the reason we use the tree explainer. We didn't use the kernel explainer here. We might use the kernel explainer and check this. Both the things will give you the same result. Model specific and model agnostic. And Shubhati, can you roam and see that everyone can do that? And SAP values here, this take little time. So if that happens, you can stop and don't do anything because see that everyone up to until this. So now it's 12:47. We almost 2 hours, so okay. So see that how that is running, 33%, 35% for me here, 38%, 38%. So yes, it should be 100%. And how many instances they explain? The total instances 3,200, and they explain 1,765 at this moment. Now 1,884 at this moment, 963 at this moment. So 64% already done. So we have to wait until this happens. %85. Okay, done. Oh, they didn't explain all things. They explained that 99%, 3,106. They stopped. Anyway, don't do anything. Don't rerun. What happens? That's all right. So SHAP interaction value, and if you see that here, you see the features 15 and 2000 is instances. And now is check the SHAP state. Okay. What happens here? SHAP values gives you 3 different things. This is the these are 14 independent features. This is the dependent features and binary, and this is the instances. Am I right, Subhashit? Instances 6,000. I don't know how that made the changes. Oh, this is a DF. I'm sorry. This DF SEF. This is a total amount of the instances, and here only training instances, because we have to split the data set, train and test. That's give me the little bit of confusion. Okay, and I just want to see that SHAP value of individual features. You see that all are individual features, all are 2 different negative and positive SHAP values, or 14 features. Okay, those okay, same way you can do that. So I made the code for you the different way, giving you the same result. Let's go that global interpretability methods. So SHAP summary plot, we see how that happens. Okay, SHAP summary plot. Okay, this is SHAP summary plot. So relationship, one of the most important features, the marital status, then educational norms and age. See how nice it is. And last one is a less important native country. And then bee swarm plot. So that bee swarm plot is, I showed you, oh my gosh. So see that how the data is distributed. That gives you the same results, that different way they give the local and global, and how the data is distributed, okay? Then we can change violin plot. We'll see how violin. But if it looks like, if you like it, you can use it. So that's the way. I believe this is a later, but you can use this also. So without layered and with layered. So I believe that I never used the violin plot before. So only for your tutorials, I just made this. Oh, that's a layered without layered. So this line is layered and this is without layer. Looks little different, but anyway. And then SHAP dependency plot. So by SHAP dependency plot, this actually I didn't mention. I didn't mention that which I mentioned only relationship. I didn't mention that to which features they can see the interaction. So that's the reason I put it by default. I didn't mention anything in the code. And they give you relationship and educational num, how many years of education. So that gives you. And here, dependency plot, age, and by default, they give the education num again. Oh my God, it's gone. Okay. So the education nums again. And here, what happens here, we'll see. So here, here is a little different way. Or means I code it a little different way. Same results, different way. And by default, they choose the another variables to whom you compare. Now, we mention this relationship and age. Before that, we didn't mention. They give you the arbitrarily one variable what the model actually want. Now is age and relationship. I see the code, age and relationship, but before that, I only use the age. I didn't mention any other things, other variables. Educational norms, means the SHAP decided maybe how that algorithm work. We'll see the white train. Sometime I put the coding, you do not need it. Oh, there's a one single instances, 790. Why I put the 790? So look at that, 790 is here or not here? Why variables? No, 790. So 790, and there's another one, row 1, 790, and row 2. Okay, look at that. Look at that 790. How the 790, but I think I can change the income, maybe 1367. 1367, that income is 1, so more than 50,000. So I change here. Oh, huh? Or there? Oh, 1367. Oh, nice. You'll see that the case, the positive. All are positive because the SHAP value is more, 74. And where's the base value? Base value is very here. Base value is how much suppose you can read from there. So base value. So see that how, I'm sorry? Almost 0. So how the changes happen? So 1376, that's the reason prediction is 1. You look at the 1 here. 1C. And 790 prediction is 0. That means income is less than 50. So it is a 790. See that where's the base value here? 0. So here the minus SHAP values. So supporting the lower income. That is the reason. So in this case, these are more influensive and negative. This influences more than this, and that negatively influence actually. And the other thing is a positive influence. Okay, this is I'm more artistic. You do not need it, and when I give you for your means you like it at home different color change. So only same plot, different color change. If you want, you can do that. If you have this coding, what color you want, just change this color. So a lot of I use the for loops. So you do not need to use the for loops in that time. So let's see that force plot for I believe that it is for stack of the data. So let it be run. Okay, see that how we change this, how it look nice. So you can change this here based on the feature. Okay, yeah, in this code they only give you the features number. You do not it's very difficult to correlate the feature number. And here also feature number. Okay, I put it there. It is not. I don't like this. So let me go a little bit up. Here, look at the range 1 to 500. So 1 to 501, so 500 data points. So what I change from these two? This is a simple coding, T explainer, expected values, and this thing. This is I use feature names here. That is the reason. Look at that, how nice it is. Now, instead of giving a number, so see the how all features are there. Relationship effect, marital status, all those. You can change this marital status. You want to see the marital status 0, marital status. You have to read the data. Then you don't understand marital status. What is 2? What is everything? Actually, they put the dummy coding. There's a reason you need to read the data. So you can do that at home. Oh God, no. Okay. Here also we change the relationship. Marital status, mean, whatever that values. I mean, you have to read the data. So otherwise, okay. Let's go here. So waterfall plot. Show waterfall plot. Show this is a waterfall plot. So we already explained this where it ends. They're starting from SHAP values as the base values, and little positive. What ends goes from here, goes from here, goes from here. So then resultant is this one. This is the most important feature, is a feature 10. So again, this. Here maybe, here again. This is also the different way you can do the same thing. One line can have that effect of your resultant. That gives you the idea starting from base value, and this is the SHAP values, a resultant SHAP values. So this is a way for the yeah. Single instance, right? For the single instance. So here there's another instance. It's a positive plus, it's a negative plus. So two different instances. Where I put the instance value? Oh, that's the instance, right. Row one is is a row actually. This row is the instance name. 790 and 136. That's same instances. So I didn't find it. The negative instance, that's the reason it aimed with the negative value, and the positive instance, it is like positive. This case actually, we can go. I'm not want to do many things because these two cases, 0.16 SHAP value minus 0.16 and plus 0.74. And what happens here? See the 0.74 plus, and maybe here also 0.16. 0.16. Done? Everyone did it? Good? Okay. So now 12:59, maybe 5 minutes break is good. 5 minute break. We can go to the next SHAP. Okay. 5 minutes break from now. Yeah. Please, can you come? Part 2, right? This one.
It should say regression.
This one.
Yeah.
Many people got it, you see.
Yep. Many people got it.
Regression here, right? So
Yeah.
regression. বন্ধ করে দিই।
Refresh.
That thing is coming here. বাথরুম গেছি, বাথরুম গেছি, 2 ঘন্টা পড়ালাম, বাথরুম গেছি, এরপর পড়াবো। এই তো পড়াচ্ছি, এখান থেকে এখানে যাচ্ছি, এই দেখো বাথরুম ব্রেক। হ্যাঁ, ওই তো আমরা যা কাজ করি। রাজুর সাবজেক্ট আমি পড়াচ্ছি। সবাই আসছে, তো পড়াচ্ছি। ধরে থাকো, ধরে থাকো, কথা বলো, ধরে থাকো। না না, ও কথা বলছে, ও পড়াচ্ছে না, কথা বলছে, আমি পড়াবো, একটু পরে ধরে থাকো, ধরে থাকো, দেখতে পাবে। Okay, so we can discuss later, okay? No, no, no.
I'll come back again.
Yeah,
Sure,
we can come
good
again.
questions.
We'll talk again after, during lunch, or even I'll be here a whole lot of tutorial and conference sessions. So the next 5-6 days, so I'll be here. So no problem. So let's go, let's move forward. And you have, would you mind to open your, this collab? If you do not open, please open, and you can let me know that when it is open. Okay, open? Good. So now you have, everyone has, suppose everyone has a regression, problem. Everyone has regression problem. Okay, I click on that libraries. So it takes little time. This is a regression problem. Before one, it was binary. So it is a classification problem, and it is a regression problem. Okay. So regression problem, you know that what's a regression problem? I'm going to explain you, and I believe that is a Kaggle data, and you click here. Oh God, it's garant. Sometimes it's not running. Anyway, so dependent variables in it is the median value of owner occupied homes, and in owner. I'm loud. Is good now? Good now? Good, good. Okay, thank you, thank you, thank you. So it is a median value of owner occupied home, 1,000 times, right? And then here it is all independent variable, I'm sorry. And see the data, how data looks like. So 506 instances and 13 features. These are the 13 features. And next, you want to see how data looks like. Data looks like and this way. And if you want to know data more, you can see here crime is per capita crime rate by town, proportion of residential land, uh, land, and then all those variables you have to read all those things, age, or distance, means all those things, and it is your median deviations. Sorry, it is the median value of owner occupied homes. So these are the things. So then your print, okay, print, you can got these things, a print, and after that, in splitting the data, same as before, splitting the data, and you split and see that, you can see here, these 13 are the features, and these are instances. So the train data instances, test data instances, okay? And after that, you go and fit your model. I use again random forest regressor. So random forest regressor. So you fit this model, and I didn't use the classifier, but sometimes I feel that they understood. If you use classifier, they understood the regression problem. They change their algorithm always to the regression and all. And after that, in printing the accuracy, you printing the accuracy, you see that train model and test model. And I just introduce here R square relation, correlation, how the R square formula. You can use mean standard error. Mean standard error means, these are error, actually deviations from the actual prediction, and a positive and negative, bless you, positive and negative, and the test and train. And after that, you now go to the, I didn't describe this thing actually, so I'm not going details of this, because you can get again, and this is the importance, regressor feature importance, sort the feature importance features, and see that which feature more important, which feature less important, and how that works means supposed to explain later. So in the SHAP, I'm only going SHAP now. So yeah, you can see the SHAP. Then explainer, tree explainer are used because the random forest classifier. Then SHAP values, obviously train model. If you change the extrain to xtest, you get the test results. So as of now, train, because why use train? Because one of the reason I use train, because I want to know the train model efficacy, means how the train model is, means give the explain the model, explain the feature. I'm sorry, so not the test data. So now this SHAP summary plot, as before, you see the SHAP summary plot. So see that is absolute value. Obviously, you do not know that which is negative or positive. LSTAT is more important feature than RM, than crime, than distance, than this see that nearly zero values, zero SAP values. So this doesn't have any impact. And now SAP summary, using SAP summary plot. So you see the SAP summary, how distributed, nicely distributed this SAP summary plot. And also SAP plot, BSWAM plot, BSWAM plot, here also BSWAM, I believe that. Oh, I use the summary plot, means this code, and extrain columns. Use the extrain column, otherwise if you do not use these feature names, you get the feature 1, feature 2, feature 3, feature 4, do not understand which feature is important. So always use this feature names equal to equal extrain dot columns. Sometimes you need extrain dot column dot features, depend on the means the method used, and extrain values. Okay, so and after that, these are BSWAM already run, BSWAM. And next, the violin plot. the violin summary plot, and I put the plot types violin. It was here how that comes, yeah. Plot types have values. Here I didn't put the plot type. Here, what is that code? Summary plots have value. Okay. So what happens? Here also I use a summary plot. Plot type I mention the bar. If you use the summary plot, if you do not mention any plot type, they give the Bisham plot. So you do not use this code, Bisham plot. Or you can use this code also, Bisham plot, you can get the same plot. These and these, both are same. And also, if you put the plot type violins, that gives you the violin plot here. So both are same. Both are same. So I put all explanation. When you go home, you can read this. And this is the correlation. Correlation between what? Between RM and RAD. So this is the correlation that the plot gives you. Interaction, I'm sorry, not correlation. Thank you, Subhashi. RM and RAD, so that gives you the interaction. And also this gives you the interaction, actually the both are same, but two different way I plotted this graph, or this plot. A dependency plot I use here, dependency plot I use here, then by default, they give the default. There's a reason I put the default. I didn't mention anything here. They give that this in RM and RAD. Here I put the RM and crime, interaction index, RM and crime, and that gives you the RM and crime. And after that, a force plot, the row number, row 1, 100, you can change it 100, maybe 10. You see what happens, 10. So 10, and you can change it 10. And see that different plot for the different instances. 200 is there, 200, and see that 200. Okay, let's do the 400 or 500. What happens? 500. That's not that's crap, because we don't have that 500 means a particular ID. That's the reason they didn't give you anything. So 400, maybe we have 365 data, so that's the reason for there's no 400 also. So how much? 339 data. So 340. So look at the change, 340. 340 also grass. 340, 339, we'll see the 339. And that gives you 338, because starting with 0, right? That's the reason. I'm sorry, 338 and change. Good. So see that how effect is a negative effect. It's a negative because this value is more important to that, means negative value is more important. And this actually I written for particular this what was there before? Remember what was there? Particular data set. I forget the name, means what row. But you can change it according to the, means I already wrote the description. So if you need to describe for your stakeholder, you can use this writing and change accordingly. And this I'm not going to show the same thing as before. And how many data sets you stacked? 500, 300 is at this time. 300, like 299, 300, right? And same way we did here. Recent plot, same way we did here, recent plot, and the waterfall plot here. Where the waterfall plot? Look at that. In the SHAP value, in this case, is a nested array. In the nested array, 3 different things are there. One is this is SHAP values. This is a base value. You can particularly get this data if you do this way. SHAP values strain dot values, you can get this. Dot base value, you can get this. And dot data is the actual data set. Value of the actual data, you get this thing. That's right. The actual housing data set, right. And now we see the waterfall plot. So you can play a couple of times, you can understand more, And the same way, it's starting from the 0 base value, not 0, base value, and there's a negative and positive and give the result in 5 minus 5.72. So that's a negative effect. So now this is the local bar plot, and local means the positive and negative both as you can see in the same bar plot. Then you can make it absolute values, and you want to see all positive. So here L stat RM, and this is negative. So this is negative. Looks like here this is all are getting the absolute value. That's put the positive. All are absolute value. So that's the reason you get that the absolute value. Now I change this thing. I change these things to the what? To the two different criteria, less than and more than. So that's the reason. Before that, age and male and female. So two different criteria are subcat means I want to see what happened in when this data set, how data set run for a subcategory, how data set impacted when I put this different criteria. So it's a subcategory. So all the data sets. So yes, and after that, what? Yeah. Oh, this maybe. Okay, this is actually just why I wanted to see that how the data looks like. This is the dependent variables and continuous data. You see that how nicely it's plotted, and the median and mean and histogram how nicely plotted. There's a little separated between the median and mean. Good data sets actually. Skewed here maybe, right? Right, skewed little bit of right side. Show this skewed here, and then here I put the two different criteria, lower half and upper half. So the median value of owner occupied homes, lower half and upper half. So lower half, upper half, I think the machine already decided by themselves, right? I didn't put anything, machine decided by themselves lower and upper half. So I believe here we can get more ideas how lower half or upper half. Lower half and 170 and upper 169. Oh, they cut it down in the middle of the data, lower half and upper half. So this is the code, but you don't have any control on this. So just two division, they cut it actually the middle portions, but obviously if the data is not you cannot if you do not divide it the data by 2, so you can get the little bit of means different values means 1 obviously, 1 more 1 less. It's odd data actually. So then you see that high here. I put the criteria. So I put the threshold is 20. So I put the criteria is more control on me. So I can control on means these things much away. So the threshold is 20. Category is like a high if threshold x more than threshold, and low if x and y trend. Means it is a function I wrote it, and if it is high else low on the data sets. So this way we did it. This way 200, then we can get that two different means sets of subcategory, 205 and 130. But this time they didn't cut the middle. They cut based on the two different criteria that I made this criteria, and how that looks like. So this looks like this way. So now you get the different plot here. Okay. Next, go to the clustering. Clustering is a correlation of means of independent variables. So this we can see that. I see how clustering this. This clustering sometimes the bias give the bias of the results, and you have to check the clustering means before. running the things, or we want to see that if there is clean clustering or not. A clustering cutoff is 0.5, or clustering cutoff is 0.5. You have to put the criteria, means, based on the things you want to know, and that's the way we have to do. Now it is like a SAP embedding plot. SAP embedding plot is a correlation, I believe, right? PCA, okay. It gives a PCA. I never used the SAP embedding plot. We'll give the PCA of how, you can explain that, how that.
Yeah, so you can either do PCA based on directly the features, but now you can with SHAP values, you have now the importance how these features play out. So instead of using the feature values directly, you can use the SHAP values of the corresponding features, and then look at how they influence. So the higher feature values are clustered, and you can see that, okay, this is the maybe an area corresponding to certain aspects or phenomena under certain subclass.
Good, thank you. So this is the things, and let's go to the next coding. Okay. Going to come. This one, huh?
I think you already sent click. I think you already sent. Remember, I was telling you.
Oh. Do you have the other one? The classification?
Classification got sent out earlier. The
Multiple regression.
sorry, the
Multi-class.
classification.
Right.
It should say black box.
Yeah.
Part 3.
You close the other codes. Okay. This is overwhelming, right? For a certain time, there's a lot of things. Maybe I'm a little faster. So, is that okay? Okay. Do you want break? Everything's good? Good. We'll take the break after this. We'll take the break after this. Sure, no problem. So it's sorted, I believe. Everyone here? Everyone is same page? Good. Let's go. So it's a multi-class classification. Already I described the multi-class when it is not binary, when it is a more than 2 class, like sepal, petal, and what is that, versicolor. So 3 different class, not the survived or means or died, or not the 0 and 1, 0, 1, 2, maybe 1, 2, 3, maybe more than 1 means 2 classes. So what happened in this case? You just run manage session. You click manage session if you get it, and click terminate other session. Please, you can click on this. Close. Okay. If you get it, you can close these things. You can do that thing. Oh, this is a Kaggle. I am not sure it's run. Oh, this one it didn't run? Okay. Okay, I actually means, click on that. Okay, again. Wait for this. Yes, good. It ran. Everyone got it? Shubhashit, someone is asking some. I'm sorry, it's ran. What do you say? It ran. Did you, anyone? This path, you can look at the path actually, right? But this, just copy paste. Did you get it right? Very okay, thank you for that. Everyone got it? Good? Okay, thank you. Yeah, you are right. Absolutely, I should have mentioned before. So next you can go here, see the data sets. So I go and explain a little bit of data. So this is the independent variables. Independent variables is Shoji, can you explain this independent variable a little more? The source plot, I only care about these things, three different dependent variables, allow, deny, drop, and four different dependent variables, allow, deny, drop, and reset both. So that is the things we put it in actually multi-class. And yeah, yeah.
So this is a internet data set, and depending on how you're operating in the network, it's a efficient way to propagate the packets across network. So this is the task for that. And given what network you're in and in what load, whether to hold the packet or reroute it or something like that. So there are four actions it can take. So allow, deny, drop, and reset both. So those are the four classes given other the network traffic your instance is receiving. So this is like a network optimization of packet rerouting, pretty much.
Thank you. Okay, let's go and see what happens. So data preparation, we copy the data action X and Y, and action actually the dependent variables. These action, allow, deny, drop, and reset both. So we drop this variable because the X and Y. And if you see that how many, you can see that way, Y dot unique. So allow, drop, deny, reset both. So this way we do. And now you have to use the mapping function that previously also I showed that to 0, 1, 2, and 3, the numbers you have to, because you cannot use the actual word, you have to give them the different numbers to mention or to go for the machine learning model. This way you can, if you want to check that truncated data, they give the first 5 and last 5. So it's all truncated data. And obviously if you check again, you can see the 0, 1, 2, 3 are no more the reset and those kind of things, allow, deny, reset, and those kind of thing. Now splitting the data set as before, and I believe that I model selection trained random, which okay, this is the actual data. I just want to see how the correlation. Here you see that the correlation here is high. Here is high correlation. Either you drop this, you can get the bias result. Means we can avoid also so many other methods you can use. One is PCA. I didn't do PCA or ICA. We didn't do anything, and just put the thing or drop these variables. The high correlation between the independent variables here, and after that, obviously random forest classifier I use. So you can change the XGB boost or support vector machine if you want. You do not need to use always random forest. And now we see the confusion matrices, how the model works, for performance is good or bad, and is a model performance good or bad. So model performance, we can see, and somebody do not like this. This way, they need the proper numbers. So that's a two different coding I put for you. So this is a proper number. And this they use that 9.4e and they 9,356. So here also is a little different because these things model run good, other thing model doesn't run. And is it to how you calculate true positive? True positive, true negative is true positive is good. True negative, I don't know how to do that true negative because there are no zero class. So is always means classified you means this way. It no means not happening class actually. So I don't know. It is very difficult to classify the true negative. Um, so I could say classify this way is a positive this class that properly machine diagnosed and other class didn't diagnose. Other numbers didn't diagnose. So that's the reason. Performance matrices, here you can see that model accuracy, F1 score 99%, very good, and AUC is a 93%. And now in this case, when you means do the accuracy or AUC, you either you do the one versus raised because three classes, one versus raised, so one versus raised, or you can do that one versus one. So it's both way you can represent the results. One versus raised. One versus raised. So I always do this way because why MDI? This is particularly this method used for random forest. That's the reason I put always MDI, but you can put the different things and means different other method. But MDI used for random forest, the ensemble model, random forest, XGP boost, descent tree, and this way. Okay. So now SAP explain I run and SAP summary plot. SAP summary plot, you see four different color because the four different variables. So you cannot see the four different color. You see the three different color because one is very less data, I believe. Did I plot anywhere? How many data sets are there? No, I didn't plot. So many less data. That's the reason I do not know whether you can see or not. And after that, you see that means how many trained and SAP. Because this is only I see. I means sometimes you do not need to more understand the data. So that's the reason you see. Not always you need to do all those things. But here, one thing is very important that SAP do not give you the overall results. SAP only give you the particular for the specific class. So the class 1, the class 1 is, which one is class 1? Class 1 is, I think one reset both. Okay. Class 1 allow? Allow. I hope somewhere I wrote it. Class 1 is how you put the dummy coding. No, you are here. Yeah, allow. Allow is 0. Not class 1, 0. Actually, we started on 0. So allow is, so this is class 1, not allow, right? Absolutely. So deny. It is a deny class. So if you want to see the allow, you change that 0 here. You change the 0 here and run this thing again. Run this thing again. So you see that these things. So 0 class. So two different. They only to particular class. So here SAP dependency plot. SAP dependency plot. They give you the sorry. They give you the correlation of source port and another features. How the correlation of this, but this correlation for the I think the reset both. These are three. Particularly dependent variables that gives you, and then it is a force plot. But see that the I is 8, so column is 8. Row is 8 instance, but the deny class, the allow class 0 is allow. So for the 0, so we can change and see that if you change the 3, both. I think 3 is both. So change and 3, that gives you the different result. Oh, this here also. I'm sorry. Here also. See that light. Look at that. That means it's a particular class, particular instance. So particular class, particular instance that gives you these things. So then this is the waterfall plot. We try to run the waterfall plot. Look at that. These are instances, 49,000, 11 features, independent feature, 4 subgroups of dependent features. So these are 1 dependent features and 4 subgroups. So 0, 1, 3, so 4 with the multi-class classification. So this is the row 50 and also is allow, right? Allow. 2 different way you can do that. So I think similar 0.16. Yes, the result is same. I actually give you the different way for of the plotting these things. Little different code, but you can use that. Sometimes one is not working, you can use the other one. So it's a waterfall plot. So I'm not going details. You already know. So this is the explanation of row 50 and category of 0. Sometime you have to put your own logic, the whether this is not actually that y4 means variable's name is here. So that's the reason we put that interpretive sign. Sometimes you have to put your own logic that or run the different explainer and check this thing whether they are working properly explained or not. So because when you go more complicated, like a multi-class, multi-level, and this they are not. That's the reason. Also, the data is so much highly correlated events data. That effect is there. So that's the reason you have to do these things very well. Otherwise, it's very difficult to explain the model. That's when I look at that. So here is an erroneous explanation. So it's called permutation feature import that doesn't work very good on the when the data is highly correlated. So this is high feature value, then there is no same all. And here also little negative values. So that's maybe the reason highly correlated data. Okay, I'm stopping here. So I believe that EL5 we did actually when we not satisfied, we ran different thing. We'll explain this thing EL5 and all those things later. So here means just try to understand that means how the different explanatory method gives you the results, how the results varies or not. So These are permutation features, but we fetch these things from different libraries actually. This is called EL5 library, but it's the same plot, permutation features. So we fetch this from the different library. So anyway, this is running. Any question do you have by this time? So we are going now more complicated things. So maybe we need to play around these things, code when you go home or with your own data and see that. But always recheck because there's a lot of fallacy. That's the reason I try to compare with the other explanatory methods. Because when it is come multi-class or multi-level, if I have time, I can give you my other research also that how we did it. But when you go more complicated data sets, so the result may not be you agree with the results. So you should know that what happens and compare trade-off, compare between the two or three different method and see that. Because this take time to run. So if you need to go bathroom or break, take a break, it's good. You can go there, and when you come back, maybe it runs for you. Okay? Oh yes, here. Look at that. Here they didn't highly correlated value. Highly correlated value. So they didn't give any plot here. So here a little bit. It should be here because if they do not have influence to the model, should be down. Instead of down the blank here, then you can get here sometime. So it is very difficult that means how you means plot this, how that. I believe that this problem happens high correlation of the data here. You see here how highly correlation. Where this plot? I'm sorry for the fast scrolling here. And for these things, maybe this is called the GINI importance, mean decrease impurity. Now we are going to discuss soon. That gives you more better results. SHAP also gives you more data result, but always you have to compare that packets here. Oh no packets down. Elapsed, look at that, elapsed time here. Least important feature here for the GINI or MDI, mean decrease impurity, what do you say? I'm sorry, what happened? Here, but here elapsed time is the most important features. There's something wrong. Okay, you understand, right? So don't believe blindly, always you, yes please. Yeah, you can do the PCA or ICA, or you can drop the variables. It is depend on the importancy. And also, some methods are working good on the highly correlated values. We are going to that part a little later. So it is your own decision. I cannot tell that this is the means robust means way to explain the model. It's a highly correlated data. So we chose the data to see that that problem might happen for your own explanation. So that's the reason we chose the data here. And let me know that also, means I give you my email address, so let me know that if you find any better method or explanation and how that works for you, you let me know so we can do that. So after this, Subhashit will talk, and this is the last part. Means after that we do one more coding, the huge coding, a lot of coding. You can see that we do not have much explanation also in our PowerPoint, and but for you, we can go and do research on your own research, and if time permits, I don't know if whether time permits or not, so we can go the next part of the research that I started with. The first part is a very easy one. We'll see that what happens next. So if time permits, okay? Oh, we have done coding online. Yes, please. Okay, I'll start for now when Subhashit come. Take it. So next is LIME. So how the LIME is working, LIME stands for local interpretability, is not global. Local interpretive model agnostic, doesn't depend on the model. And I can show you that they use LIME for the global, but you feel means when we run again, some features got changes. So I never use or never recommend anyone to use the Lime for the model agnostic. So this is that this is a glass box. It uses glass box model explanation, and then this happens. So now, Shubhashit, you can go and.
So we are looking into another model agnostic. And over here, Lime is a very local model. So what it does is that, let's say you want to explain the plus, which is like highlighted over here, that particular instance, how the model decide whether it's like positive class or a negative class. And what we do is like we try to fit a local model, which is like a simple linear regression because they are easy to interpret. And in that boundary, and you see the complete decision boundary of the model distributed over the whole data set. We don't have that picture. That's just a hypothetical situation, like this is how the complex decision boundary is. And we try to explain with a linear regression or something simpler model, like for that particular instance. So what we do is that we'll generate synthetic data. So that region might not have enough points. So we are going to add some perturbation to the distribution and sample from the distribution. And then what we are going to also do is like weight the features. So the synthetic data that are closer to the reference point, they're weighted more compared to the instances that are farther away from the data, from the reference point. So it can be defined by three different aspects. One is your original model, F. You're trying to explain that, the function output. And you are trying to use a surrogate model, which is the linear regression that you want to fit at the exact location. And then this is a sparsity constraint, which is like a L1 minimization norm, where it says that use the most minimum number of coefficients or minimum number of splits in the decision tree to explain the data. So we don't want complicated model because then we become the monster that we try to beat in the first place. So over here, we just showing you how regression works. So pretty much once you fit the model for different features, so x1, x2, x3 different independent variables, you get, after the model is fit, you get beta 1, beta 2, beta 3, the trained weights, and then you can plot them and look at the histogram of or the bar plots pretty much of which features are more important and less important, the driving factors, and that's how you derive which is the most important variables. So over here, this is like a whole summary pictogram of that. So you have a manifold of the data where it lives, where the model predicts, the prediction is given by the heat map, and then you have the distribution of the features, which is like a very high dimensional space. And then you pretty much pick an instance that you wanted to explain, and then you populate that area with synthetic data because that area might be sparse. And then you also ask the model to generate the Y prediction for those synthetic data. And then you use a linear regression model to fit that synthetic data with the generated from the distribution and the model prediction. And then you explain with the weights of the linear regression. So that's pretty much the beta coefficients. Okay, so this is the beta coefficients that you get, and you can explain things. This is the weighting factor, like how much should we weight. So this is like a hyperparameter. So if it's large, you get a bigger circle. If it's small, you get a narrow circle. And then you can get different linear regression fit for different kernel size that you decide to fit the region for. And then you can definitely get an explanation like you can see over here. For that particular instance, it's showing that glucose is lower, so it has a diabetes chance in that region. It has diabetes because it's in this region, and then there's age. For those are the instances, it has the reason. You can also do for Lime for images, where you segment the image into different, not segment in the sense deep learning segmentation, but just cut it with different random masks. And then what you do is like you try to fit a model. So what you do is like you mask the different regions and pass it to the model, and then you are going to get different output. So this is like a weighted uh, plot for which masks are predicting how much, what the model is trying to predict, whether it's predicting the correct class or not. And from here, you can identify which mask is most important. This is identifying errors in Lime. You can also predict that the model can be accurate, but for wrong reasons. So, for example, this 20 News Group article that is classifying articles based on whether it's a topic on Christianity or atheism, and even though it classifies for the right, given the prediction over here, the classification is correct, but from the model explanation, you can see that it's highlighting words that doesn't even related to the model prediction, like .edu and .ntf. Those are the wrong reasons. So you can also, this is a downside that I'm trying to explain. Since Lime generates synthetic data, if you do it repetitively, there is a chance that you can get instability as it is shown over here. And it generally occurs when you try to convert Lime to global. And I'll show you how you can do like force Lime to act globally, even though it's originally meant for local explanation. And these are some explanations, like Lime is specifically for local, but SHAP is both model agnostic and model dependent, and it has different aspects in it, like local plots and global plots. And Lime has a very specific local perturbations. It has a very specific mechanism that SHAP does not rely on. Okay, so now that's a quick wrap up on Lime. We are going to go over permutation. This is another global explanation. This doesn't have any local. It's a model agnostic, and it ranks which is the most important feature. So its idea is to take out a particular feature and see how the model is going to perform, or how the model is failing in predicting when that feature is not present. We are not going to literally take out the feature, but we are going to randomly shuffle that particular independent variable column, and doing so, it induces a randomness that kind of destroys the information that the model can rely and predict. And now you can look at the prediction error. If the prediction error after random shuffling is too large, then you know that this particular column was something that the model relied on to predict. So it's an important feature. So that's pretty much how it works. This is just a same reiteration of the idea. It's shuffling, and we estimate the error. But since this is a randomized algorithm, what we do is that we just don't randomly shuffle once. We shuffle it a couple of times, and then look at how the error changed for k number of shuffles, and then we average it out. What's the prediction error changed for the k different shuffles, and then we get the importance based on how large that error was from the shuffle. And now this is model dependent, and it's a global explanation. You don't get local explainability from MDI. Yeah. You saw feature 3 importance, the green bars, if you recall. And this is a more detailed work through how that is being calculated. So over here we have 2 different classes, cat A and cat B species, but it could be anything, and you decide based on fur coat color or something. So you decide a criteria, and then you split the variables into 2 different subgroups, and you can keep doing that till you get to an homogeneous point. Now the question is like, so there are a couple of things. This is a splitting happening in terms of target variable. So this is the root node. These are the blue ones are the decision nodes, where you're making the decision till it reaches a homogeneous node, where it's like purely comprises of one class, and there's no further division you can make. Or if you reach a certain depth of the tree, so you want to keep your model not too complex to avoid overfitting. And then there's something we call node purity. We decide our nodes addition based on something called node purity. So we want to make a decision where the split is going to result in a better separation from the mixture of samples that resides in it. So, and there's an estimation that we can do by how to call forth that aspect of mixing and node purity. So here's a toy example that we are going to use to specifically quantify this concept of node purity using this mathematical term called entropy. So you have a distribution of 15 students who have certain status. So your objective is to explain whether the student is going to pass or fail, and they have different other attributes, whether the student is going to has a mathematics background, computer science background, or other background, and whether the student is enrolled in other online classes, and whether the student is working on or non-working student. So what is purity? So over here, the entropy is pretty much probability of that particular class multiplied by log 2 of that probability of that particular class. So if you have 3 in a, maybe I can show it to you over here. So let's say in a container there are 50 blue balls and 50 green balls. So the probability of you randomly picking one is going to be 0.5 because it's completely homogeneous. And the entropy is going to be 0.5 multiplied by log 2, 0.5 for the picking the green ball, and this for the blue ball, and you get equals to 1. So, and when you have completely separated out container, so for the other class, you are going to get 0 probability, and that's why it's going to end up getting 0, or vice versa. So for here, we are going to first look at the purity of this node. So we have 8 by 15 is the probability for pass, log 2, 8 by 15, and then for failed, it's 7 by 15. And you calculate it's roughly close to 1. And then we decide to split based on working or not working class. And let's see what we get. Similarly, the same logic follows. It's 3 by 3 plus 6, which is 9, the probability for passing. And this is 6 by 9, which is probability for failing. And you do the math, you get 0.9183 for the left node, that's the purity, and for the right node, the purity is 0.65. Okay, so now I'm going to average it based on the weight. So over here we have 9 splits, 9 students over in this node, and 6 students in this node. So we're going to weight by 9 by 15 plus 6 by 15. So this is the actual weighted entropy for these 2 nodes together. Okay, so now that we have the impurity of this node, these 2 nodes summed up, and the parent node entropy, we can calculate something called what's the information gain, or how much entropy decrease or impurity decrease we obtain by doing the split. So we just subtract the impurity of this node from the 2 other nodes, and we see that the information gain is 0.1858. That gives you that this is the information gain by doing this kind of split. And this is just better represented in a tabular form for you. Okay, so the next thing we can do is that what about the other features? Can we predict anything better? And turns out that we can, and if you look at the entropy of these 2, and if you split the data based on student background, you get 3 different nodes because there are 3 different classes, maths, computer science, and others. And you can get pure nodes for these two. That's why you get 0 entropy. And the entropy for this is 0.9852. But you then do a weighted average across all these 3 nodes, which you get over here, 0.4598. And you subtract these two, and you get 0.5370. So the information gain based on this split from the root node is much more compared to doing the splitting based on the working or non-working criteria. So we are going to choose this compared to any other. So like you can do the math for other nodes too. And that's what happens in decision trees in the back end when they are getting trained. There we are going to look at different individual features and see which split gives you the more information. And that's where we do our first split. Now the splitting continues. So we pick the nodes that are ended up with non-homogeneous. We did not get a very clean picture. So how can we parse that? So again, we are going to do the splitting. The logic is almost similar. So we are going to choose working versus not working. We're going to, this is the entropy of the parent node over here, and then this is the entropy of this node, and 0 is the entropy of this node. And when you do a weighted average, you get 0.4636, and you do a subtraction, that's the information gain. And which is much less for if you decided to split based on whether the students are enrolled in other online classes or not. And over here, you can just reiteration of the same logic. This is much less for the other feature. And we keep doing that till we get a very homogeneous split. So this is entropy. We can also replace the whole concept with another formula, which is GINI. And that's what happens in permutation, the GINI importance and the mean decrease in impurity. That's the actual formula that is being used for splitting. There are other formulas that also works well, but these are the standard ones. And for random forest, when you have different trees together, what you do is that to identify the feature, the most important feature, you take the mean decrease in impurity across all the trees and then sum it up based on which level they are used to do the splitting. So remember the weightage we used for population. So if they're at the root nodes, they're splitting more instances. So that's why they are going to be more important compared to if they are in the lower nodes. So that's the weighted average that you get. And this is just a code to show you what happens in GINI. And this is just the plotting that we are going to go through, showing which features are most important and which are not. Here is one instance that where GINI is going to suffer. So over here, we are going to show you that MDI is biased towards high cardinal features. So if you look into some of the earlier things, we are introducing a couple of random variables. One is a random categorical variables. It literally says x in bracket random underscore cat and x in bracket random underscore num. So that's the continuous variable, and the other one is. Okay, and what you see is that like when there's a high cardinality where you have this continuous variable, even though this is a random variable, you are going to see high importance in picking up in the MDI importance, but that is not quite the case in permutation. So permutation is kind of immune to this kind of high cardinality of features. So remember that when you are using GINI importance. There's another interesting nuance is that when, as Dr. Datta mentioned before, if the features are highly correlated, if you shuffle one of the feature column, the model is going to rely on the other feature, and it's going to still give you no error in the model prediction. So that's what the MDI suffers from. and sorry, the permutation suffers from. So the way to solve it is by using clustering and picking one of the important features and discarding the other among the correlated features. So, and once you do that, you gain back that importance. So not everything is zeros now. So previously you would see everything was lined up into 0.00, so no features are important. Now we are going to go look into briefly into other things. So this is called ICE plot. It literally, what you're going to do is you're going to take a particular instance and vary the variable feature, like just change the feature value and look at the model output, and you're going to see how for every instances you're going to see how the model is giving if you change that feature. And then if you sum these things up and do an average, what you get is called ICE partial dependence plot. And you can also look into how two different features can impact. So the heat map is the model output. So you can also look into the interaction of the plots. And then there is ALE. PDP also suffers from correlation, but ALE kind of removes that by binning and different features into smaller intervals and looking into the intervals, and it eliminates that correlation problem. MDI is similar to permutation importance. What it does is basically, instead of randomly shuffling the features, it introduces a small error and then look at the model's change in prediction and weights that prediction by that delta, which is the error or the perturbation that it introduced. And you still get the same thing. So these are the different things that we used. You can pull it up. That's the only remaining, right?
This one.
Yeah.
Others?
Yes, send. I will just briefly send it to. What's the time? Did he send? Okay. Give me a minute.
So did you get it? Give me the mic. Okay, this is the last part, and then if we have time, I hope we have time, 10 at least 15 minutes, we can show our next presentation. So hopefully, yeah. No, we don't have that other recording.
So if anyone has the issues, let me know. Okay. I'll just go here and share you the link. You can type it.
Good. So let's go a little bit. Let's go a little bit of this. And this is a huge coding. And I believe that I'm right. The same data, 50,000 income, either means more than 50,000 income or less than equal to 50,000 income. So this is a, don't run again, run all. If you run all, it will be crash very easily. I hope it will crash also. So the important libraries, always you run important libraries. And after that, it'll take time. And when it runs, so you can download the data sets, the census data set, that same data sets that we used before. And after that, you just read the data, and 2000 until 2000 data. Only I chopped it, less amount of data. And I'm not going details of the data, so you already know that before, that these are the variables, and age, capital gain, capital loss, and that we want to predict that income. And based on this independent variables, we want to predict the income, whether less than equal to 50K or more than 50K. And then this is the target variables. You see this is a binary as before. Imbalanced data sets, I'm not doing anything here. So again, you can try, if we use, you can do that. This is the same code as before. So you do not need to, you already know that. So yes, so just run, and 1.5. Hope this one, no. It's a little lengthy, this one, and but bear with me, and hope we can make it finish. So 80-20 we train and test, and then a model, a random forest, same things. Means we do not want to change. We keep it random forest, but again you can change it according to your need. And confusion matrices. So model performance, actually, couple of time model is not good, 43 and 14. Model is not good, and then print accuracy, and these things also. So model accuracy, and after that model accuracy is not bad, but not good too. See that if you see the two different class, this class one, I think more than 50,000. This is class one. Model accuracy is not good. So some point model accuracy is good. Some class model accuracy is not good. But if you see the average is good. Anyway, 89%. So don't worry of this matter. So if you use extra trees, hyperparameter tuning, different way hyperparameter tuning, you can get the different values. So this is the way. So as Subhoshit explained the lime, so I'm not explaining this lime. So if you have to pip install lime, then you import lime, you pip install lime, then you pip install lime, then you import lime and a tabular, and then you have to create lime explainer as SHAP explainer, the similar way, lime explainer. And suppose you already mentioned that the local is row 50, and then you do the explanation. Row 50 means the instance 50. See that particular instance, and they do give that two different category, less than 50K and more than 50K. Two different category, and you see that which features supporting which. So this feature supporting that the prediction should be more than 50K, but most of the features they're supporting that the feature will be the less than 50K. So this the resultant goes to less than 50K. You see that here I know a little bit of dark, 0.99, and more than 50, 0.01. So it goes to less than 50K. So as I mentioned before, Lime, Subhash also mentioned many times the Lime is local, but some way they try to do the Lime is global. You tell me, means when you go back your home and read some, means, different evidence if you get it, whether Lime is, means, globally, Lime is good or bad. I never use Lime global, and keep this way. Don't click anywhere. It take time. So. Uh, it take time, so clip this way, and I saw that if you run couple of times same thing, you can get little bit of different feature importance. So that's one of the reason I do not means, see much, means, usage of Lime is global. I never see much this thing Lime is global. So keep this way until it's run completely. You cannot get any results if you click the bottom one, because until you have to finish this, then you can get the results. If you click couple of things, it will crash again.
Yeah. Okay.
I'm making little hurry that we'll see you again one more research.
We can explain even without running, right? No.
No, we cannot explain. You can wait.
The plots are not there.
Plots are
Okay.
not there. That's the reason.
Okay. All right. Okay, so here is instances where you can use Lime as a global plot. What it does is pretty much in the behind the scenes, it's going to do a local explanation over every instance and then look at the feature importance averaged across all of those features, all of the instances that you wanted to explain. So doing so, it runs into an issue. You can see that it's always giving you some sort of a different explanation. So one of the reasons why these are just different explanations that it generates. So Lime could be a little not robust. There are other libraries that are trying to address these issues using variable, the kernel size and everything. So you can explore more later on if you feel that Lime has some important aspects with the surrogate model. So I like the feature, that aspect of Lime, because it uses surrogate model. So right now I'm using another thing called permutation importance. It's also going to take a little time. So over here, it does the algorithm behind the scenes, so you don't have to implement all that from scratch. This line is standard error. So remember, it's a randomized algorithm. We do k number of shuffles. So over here, it does calculate that somewhere. And you can get to see the error bars as well. And then this is also same thing, plotted in a different way. So over here, it gives you the error bar in the other direction too. It was just clipping off in one direction. And it also looks into the negative side. So over here, you can see like sometimes it can go in this direction because some shuffles can improve your model performance. So that's why you might get that negative thing going in that direction. Okay, this is pretty much MDI. So once you do that, like you look at model.feature importance, this particular code is not going to come with other models like KNN or SVM. This is particularly inherent with random forest. So like I showed you, random forest literally uses GINI importance to calculate how to train itself and make the decisions, and you literally can grab that GINI importance to calculate this. So it is inherent within the model to make this decision. Then there's LE5, which is the similar library called Permutation. I'm just showing you different libraries that exist, but you can just simply use the other permutation library that I used before. There are no differences, at least to me. I did not see it, but we just kept it in case there's something important that you find. You can also use, interestingly, you can use LE to explain local reasons, which is not quite explainable using just permutation importance, because it does global shuffling. So this is just running. Okay, so it's pretty much like you can compare with that. This is not the feature importance, but permutation importance. You see education norm relationship, age, marital status, education norm relationship, marital status, age. Wait a minute. Yep, there's a little shuffle over here. So I think sometimes it's like the way the algorithms are implemented. Maybe it's doing more shuffles than the other library that's using and how they normalize things. So it's kind of interesting to just explore. And this is kind of hard to see, so you can highlight and you can see what it's doing. It's trying to, for a given instance, I think globally it's actually giving you what are the values of these bar. So you have rather a quantity rather than just looking at the bars. It's more analytical. I don't like how faded it comes. It used to be not like that, but I don't know what changed. And this is just for local feature importance, so you can particularly pick. So long scroll. I don't like this. So over here you can choose a particular instance, and that's one of the good thing about SHAP is the LE5, even using local explanation, even using permutation, you can explain locally. So over here, that's pretty much, this is for explaining a couple of other instances, just to show you. Yeah, that's pretty much wraps up the LE5. Now we are going to run some partial dependence plots, which you have seen before. It's pretty much changing the variables. So not all these variables are present in the data set, but you can literally plug those variables and see how the model pretty much outputs. And then you get the whole plot. And you can also look into interaction. So it's again running the same thing, and also for interaction. So it's going to take a little while to run this. And interestingly, ICE actually, PDP can be, partial dependence plot can be derived from ICE as well, because it does the perturbation So this is the heat map as I'm showing you for education num and age. The heat map shows what's the whether the I think this is the adult data set. So this is the model prediction how much the person whether is earning less than or greater than 50K, what's the probability of it. So as it goes up or higher education, you can see it's brightening up. Okay, this is ICE plots. Wait a minute, did it run? Yeah, it's running. And these are just different libraries that you can use. PyAL for running ALE. Okay, so you can see for each instances, if you change the education num, for some instances you can see the model is going to give you negative output even though the education num is decreasing. So these are some of the instances, very important to see. Not always having more education is going to result in more income. So these kind of things you can more explore with ICE. Partial dependence plot has some downside. So if you are going to have a correlated feature, it's going to run into errors. So PyL looks into like small bins of the features, so it's going to fragment and create smaller bins and look at perturbing how if you change from here to here how the model performance change. So it does some sort of a window-based smoothing in a small interval. Then there's other plots. We can also use alibi to do the same thing. So there are different libraries that comes with different aspects. We haven't explored too deeply because it's for you to go and explore. We just kept it here to show you different packages where you can pretty much get the same plot, and it might come with some other important, like maybe the output is more looking better. So those kind of things is very important that you play and see which library is making more sense to you as you look into the more important nuances. Oh, cancel, restart session. It crashed. Yeah, we have to run from beginning, but I'm just going to. So pretty much these are the libraries you can play around later on at your home, but this gives you all the ballpark that you need.
And also the Daleks, there's no chance to run now,
Yeah,
or you can do a little bit of, we'll see that.
you can click run all
Yeah, yeah.
around and finish the presentation and see if you can go back to it.
We don't need to run all. We can need to run before accuracy. Yes. Look, maybe we can run 10. Drop run. Come here. Whether run before.
Run all.
No, run before.
Oh,
It's not there.
I think click on runtime, insert runtime.
Insert.
No, yeah, next, yeah.
Run
Run
before.
before.
I believe these are good. Run before. Yeah.
Okay.
So. You talk. Where do you stop?
I think we are doing something else. Go down. Yeah, this was installing. So pip install PyL. I think this one also ran actually.
You did.
Yeah, I think where it crashed is this one. Yep. So maybe run the code before. It'll fail. Maybe you have to. Yeah, do pip install alibi.
By the time any questions you have, you can talk to us. And I know that we don't have PowerPoint, all those different methods. So because we are still exploring, And I am giving you the code if you got this thing, and very few people use that, not very much popular, like SAP, Lime, MDI, those are very popular method, and this is not that way popular. So, but anyway, if you feel that there's any good things, obviously you can use, and not many libraries you can get it and learn again. So many library you can get it for this, but couple of plot looks like very good, but I didn't get much time to explore or compare. Maybe we need to compare those kind of things and see that how that does work. So this actually showing you all variables, how that uh, model output affect the model output, and because they're showing you the 4, 4, 12, no, 1, 2, 3, 4, 4, 12, but we don't have this, means that many variables. That's the reason they stop somewhere. So you can see the blank and these things. And also here I will see that how that goes. And is a Morris sensitivity. And I look at Morris may be a little bit promising, means but you can explore and let me know that how that. And Daleks actually I got just before coming here. Certainly I discovered these things, but how people feel that on this means on the new method, you might need to know a little bit of validity, or people opinion is need to read some journal articles. So I'm not going here, but uh, this time we use the XGB classifier, XG boost classifier, and then people install Plotly. So they are dependent on the means Plotly. They don't have that own way to means plot the feature important. This is a local. They're giving a local importance. We'll see that. This is done, right? Last one. I believe last is. No. There's a plot. Yeah. This is a plot. This is also very nice for local explanation. So this breaking that positive, negative, that breaking. So you can explore and let me know if you get anything. How people think you have to read some journal article and then you have to decide which particular method you want to use. So I have 15 more minutes. So we'll see that how I can show you our research little bit that we did based on this. And also, did you see that? Also, before going this, um, next, and take this two QR code, and take this two QR code, and this is actually comparison of couple of SAP, MDI, interaction plot, and what's permutation feature importance. So those three things we compared, and particularly the severity of disease, not mortality. Mortality we only explained I think SAP and MDI. And also yes, I made little mistake that I told you that interaction happened by SAP only. SAP library you can do obviously, so we show partial dependence plot also do the, but we never get a chance to check those things. So I do not know so whether they do or not. So next is Just 10 minutes maybe I can show. No, I have no idea. So we present actually this is the in SD, it is statistical and data science. Oh no, I am not to go this way. Yeah. No. Yeah. Scroll. Uh, no, that happens before that. There is another case. Still, we are not sure how multi-level classifier. When you use the I showed you a regression model. I showed you the binary classification. I showed you that multi-class classification. But another things multi-level. That means first I can explain you what multi-level actually. So and also Subodh is presenting some of the day means dilemma of multi-level. I believe that what's the session name? What's the session name? So you are presenting some of the day. So multi-level is this is the way multi-level happens. Look at that mortality, ventilation, ICU, IMCU is a means lesser. This is a worst when patient died. A second worst, then second worst. This is still better because IMCU is a less dangerous than ICU when they put ICU. So this is a patient ID, so anonymous data. You see that patient, all patient hospitalized, patient doesn't need anything, and zero mean patient discharged, one means patient died. 0 mean patient never have this, one means has. All are same. So when you see that this example, so patient doesn't need IMCU, patient need means ICU and diet. Here, patient need IMCU, then ICU, then ventilation, then discharge from the hospital. So this is the kind of pattern. This pattern is the Venn diagram. See that how pattern looks like. So this is the how patterns looks like, and then we are trying to predict the pattern that this pattern is either 0, 0, 0, 0 or 1, 0, 1, 0. How many patterns? 24, 12 or 24? 4, 6, 8, 16 pattern. 16 pattern. So this 16 pattern, how we means I'm not going details or chain classifier how that works, and this is the accuracy got using this is a kind of classifier named multi-level classifier. So we use this multi-level classifier, and then the SHAP plot. When you put the SHAP plot doesn't give that means complete this kind of plot. The problem happens, and even that is the plot. See the 0. So I don't know, I didn't explain maybe. So 0 means the neutral point. So this side, if it's binary, so 0 means neutral, this side is died, if you go this side died, and this side survived. So then you can see the variables, and if you compare the variables with this dummy coding, if it is dummy coding done by you, not if you use that 100 encoding, the computer made for you, you do not know that what the coding they do for you. Dummy coding, I willingly made it. That's also introduced some biases to the model, but I made it to understand this thing. This means like if it is a diarrhea, they died. If it is not diarrhea, they don't die. Sex, male. If you see that one is male, all hot color goes male is died, more prone to die, and this female is not. So like same way, and if it is binary, it is easy to explain. If it is not binary, how do you explain? If the multi-class, how do you explain this? Multi-level, even if multi-class, I showed you that model, this kind of things giving you single means, classification cases. So if it is 4, so that's the reasons we put 1, 2, 3, 4. But multi-level, they give you this way, how you classify. Do not know that. And also, no, I'm not going there. Also, this is actually the things, so we are not sure. I'm not going to make more complicated this manner. So this is one of the dilemma, and hopefully I hope that you never use the multi-level, right? Anyone use multi-level? No one use multi-level. So it is huge use for, means, when patient is when they're in medical cases. And this is the explanation when you see that one versus race, 3 different classes. One versus race, so cat versus all. So cat versus means, very small, so you can see one versus all together. One versus one is kind of 2 pieces, one versus one, one versus one. So this way we did it. And also, and this is a case I told you that is a multi-class confusion matrix, also very difficult to understand the how, means, you can get 2 positive, 2 negative, 2 positive, you go to false positive, false negative, how get the 2 negative? Means we do not know how to get the 2 negative. So those kind of dilemma is there. Another things, another things in these kind of cases, you can, it is actually multi-level, not multi-class. You can make the multi-level to multi-class. This way we did it. So multi-class, like, 3 is more dangerous than 2, then 1, then 0, and see how the distribution of the data. So you can classify both the way. This is little easier, but there is a lot of overlapping. In that overlapping, when patient also have ICU than MB, and I put the criteria, if it is MB and ICU, take MB, highest level. If it is ICU and IMCU, take ICU, highest level. So this way we made it multi-class, but many people opposed me that means, it is not actual the things. Many medical persons, they opposed. So this is actually the multi-level. So you forcefully made this multi-class. So this is the things actually means, the dilemma, and hopefully in some other way you can make this possible. We are still researching on this. Okay, one more things I can tell you, this thing. So we classified all are binary, same data set, remember that. So this is the ventilation, this is ICU, the IMCU, all are binary. And we compared all individual class. We compared MB, ventilation, ICU, and this. See that arrangement of the variables here and arrangement of the variable here is similar. I cannot say same. Diarrhea, age, what else? Diabetes, sex, diarrhea, age, diabetes, sex, race, similar, but it is not similar here. So that means the MB and ICU same in nature. Those are more dangerous. They need ventilation. MB means ventilation, mechanical ventilation. So those are, and almost all ventilation happens in ICU. So maybe that's one of the reasons that there's a very good feature analysis we got from using the SHAP summary plot. If you go to our second our journal article, you can see that explanation more. And another things is the last things I can tell you this. This also compare. I didn't see this plot because this plot is you have to made using the definition. I didn't. There is no inbuilt SHAP plot on this. So this is also, you see the first, the most important, the least important. But you see that first 10 features among the 20 features, first 15 features give the 95% of model explainability. Any of them, See that 95, little more, little less maybe. So what happens in this case, if you run this model with the first 15 feature, you get this accuracy. So means that helpful that when patient goes to doctor, doctor may need all means features to know that, and most of them are lab test. You make the patient wait to send the blood, urine to the lab or other things to the lab, and wait a couple of days. Patient maybe get more sick. So you may see 10 important features and means take the precaution for the patient, like patient need maybe ventilation or ICU or IMCU. So then you can may check all those things, but your management will be quicker. Still, we are working on this, that how that works, and one of our it's a mortality. It's a mortality binary, yes or no. You see that these features, these first 15 features give that 90 something model explainability, and among these 15 features, if you check this, you see that I showed you first means when I started the presentation this morning, that these three groups of variables. One is characteristics, then comorbidity and medication. All groups of variables, all are there within first 50 feature. Characteristic, comorbidity, and medication. See the medication. So that I can tell you that if you get this kind of things, so you have three groups of variable model, take all those things and explain the model, and first 15 feature enough. It is very transparent and reliable. You can say the model decision. Okay. So what's the time now? We are mostly done. Three more minutes. Any questions?